Okay, we meet again. Waiting for Twitch to show green light. It often is green. It's just delayed, I think. So, okay, now it's really green. I'm trying another platform in the mix today, LinkedIn. I'm just gonna do a quick check whether the broadcast is indeed on the page. Don't see anything. This is something I'll look into some other time. So, safe to assume LinkedIn is not accepting the footage. We'll turn it off. We'll continue with the stream. So yesterday, the last hour or so of the stream, we were looking into some kind of calculator for determining whether it should snow or not. So we were looking at scientific articles and some basic online calculators as well that shows the possibility calculator, right? One example that I found was posting the data to backend. I wasn't able to reverse engineer because I couldn't see the code. Let's say it wasn't part of the page where I could see it. So then the rest of the night I read a bit more. I think eventually things start to look more like they were converging. Wish I would open it in a new tab. Okay. So things look like they were converging to a basic graph, which this is not. Okay. Let's look at this PDF file I downloaded. Quickly skip. This was very technical. This had this kind of equation, and then later in the appendix, here, similar equations. This one was a cubic equation, and then you have the derivatives here. Some of these values are fed into other equations, that sort of thing. This still felt technical, although there's something familiar here, this number that was used in some of the evaporation equations. But that's a different day, different topic. It was done a while ago. We may have to revisit it. But there's some familiar ground here. However, only I could find that yeah, things look like it'd be as simple as a linear graph. Right? The basic assumption is that which is not entirely correct, but this paper is investigating whether it would snow over 0 degrees. And in fact, the probability of snow is decreasing as the temperature is going over 0. And when you get to 8, 10, these are different stations. I think there's 9 or 10 here. So basically, depending on the elevation, there's some shifting here, but either way, this is the zone where the probability is approaching 0. So if it's 2 or 4 degrees Celsius, you still have pretty much 50% chance of snow. That's what the studies showed. What is kind of weird in this result is that there's 100% chance that it will snow when the temperature is below zero, and that is not correct. Uh, I mean, I have first-hand experience that it's not correct. Pretty sure a lot of people could share the same info. Um, it still depends on humidity, which is calculated, which is a relationship between air temperature and dew point. So how saturated the air is, hence how moist the air is, that kind of thing. So when there is enough moisture in the air, and you can't pack more moisture in between air molecules, let's say, then things will start to look like they are going to precipitate. It's as if you have a glass of liquid and you mixed in sugar or salt, but you lower the temperature of the liquid. Things that you were able to dissolve into the liquids is no longer going to find enough space to like hide themselves. That's like chemically or physically how it happens. Things will start to look like they are just raining in the glass, like there's precipitation. You'll see stuff accumulate, solid stuff accumulate at the bottom. So rain or snow is essentially the same thing. So humidity has to play a factor in how much room there is for things to flow easily, or basically not find any more space and sort of fall out of those molecular space. So without the scientific without getting too scientific, but still keeping it pretty much as simple as this, need to come up with a way to provide a few values to get a boolean result. It's either false or true, it snows or it doesn't. Then there is the remaining part about data cleanup is left over from yesterday. Another interesting thing is um, this graphic, or the results that are represented in this graphic, is kind of a remedy to what I was pointing out earlier. If you look at this graphic at the bottom, one might think that below zero you always have 100% snow. Turns out, well, it isn't, we know, but then you go into this probability space too. What is missing here, which is sort of misleading, that this probability of snow, this axis, should actually be, I don't want to say swapped one by one. You can't just raise this title and say humidity, like this is 80%, 60% humidity. We can't say that. The distribution might change, but the sentiment is the same, that below zero, the higher the humidity, the higher the chance, hence more dots. So that's the equation we have to come up with. In other words, something like this. We kind of did it to a certain extent. This was used to determine the snowflake type. The graph is kind of weird because the more you go to the right direction, the colder it gets. Normally, you should be seeing things that are growing up. But anyway, in this case, it's the coldness axis. Depending on the humidity, the snowflake types are changing. So we need something like this here. And then, well, in this case, this graph is done, right? So left to right, things are growing. So we gotta find a way. So this is a relatively short article, which is not going to talk about humidity, I believe. One of the papers here they mentioned. This looked interesting, but then wasn't really what I needed. Of course, the ultimate goal here is to clean up the mess that is missing data. There's a lot of snow data. Where is AL? This is showing that in the last 6 hours there has been 1 centimeter of snow depth, but they don't mark it every 6 hours. That is missing. Let me run the filter so we can look at the refined data. There. So this AA1 is the rain. So they, even if it's 0, they still mark it every 6 hours, which is good. They don't do that with the snow. So there's a lot of missing data. Normally this should all be marked 0, 0, 0, 0. Well, that's kind of what I do after the fact. I fill these out with the kind of backtrack. I distribute this 0 to the previous 6 hours. But for me to do that for the next known value, the values get infinitesimally small. Or from the last day of snow, let's say March or April, to the first day of snow in the year, like November, if you follow the same logic, you assume there is some snow in July, let's say. Some very tiny value for each day between late March and early November. So the threshold concept was introduced, turned out to be arbitrary. So the decision was to clean this up in a more informed way. Hence we are here. So we gotta perhaps do something like, well, for this hour, here is air temperature. Sorry, this is dew. This is air temperature. And from these two, we could we could calculate the relative humidity and the relationship between relative humidity and this. We could determine whether it snows or not. If it does snow, then I'll find the next value here. But the benefit of this over the blanket assumption is that most likely we will have false here, like we will have no snow. Now we will have some snow in this 6 cases. Then the range will be small, and this value distributed over a shorter interval will yield better results than distributing this over a longer period like this. So that's kind of what we gotta do. So let's get with it then. Where was that other graphic here? Yes. So we need to figure out a way to change the meaning of this probability, base that on humidity. There was another article that I found last night, but I'm not sure if I recorded it. Implications during I open this, the probability I open this too. And this is already a document, so I guess it was a Google search, right? There's no probability calculator. I think I remember. This has a link. It's talking about the science of freezing point and such. Okay, this graphic in my mind corresponded to what I was seeing. I'll zoom out a bit. This, or this is sort of the tidied up version. Okay. If you look here, I'm gonna remind myself first what these lines were and then explain them. And also read it from the screen too. The red line is no melting line. So below it, snowflakes cool by evaporation more than they heat from the environment. So there is no chance for the snowflakes to melt below this red line. However, like I said, it's also about humidity too. Let's keep reading. I think something will click as it did last night. The magenta and blue lines are 1 and 2 degrees above no melting lines. So it's like 1 degree, 2 degrees. Okay. Between 0 and 1, it mostly snows, whereas it mostly rains between 1 and 2. At warmer temperatures here, or you don't care about this, so we are in this sort of zone, warmer temperatures. Let's take the second half here. It rains. The green data points are events collected by these two monsieur in Japan. Okay, so it's hard to see these dots. I zoomed in and looked at it carefully. So these are mostly circles, green circles, and it's rainfall. As you get close to the blue line, you are in between magenta and blue line, you start to see sort of a vertical shape, which is sleet. This is when rainfall is turning into snowflakes. The raindrops are, in a stupid term, they kind of look heavier, let's say. Okay, solidify in a sense. That's mostly what's happening in between these transition lines. Then, so in between the magenta and the blue. And when you cross over magenta towards red, you see those sleet shapes turn into more square, more X-like things. There's a bit of there's more mix of sleet and snowfall here. There's more rainfall and sleet mix here. This is all happening in a higher relative humidity section here, but never here. Then when you cross the red line, it's mostly snowfall. It's mostly those square or X-like things, right? So we could assume, based on this data, it's 60 here, so it's 50, 55. 55 is sort of the cutoff zone. The same kind of danger here happens too. There is no data here below 0. So now are we supposed to say, well, if it's below 0 and over 55, it always snows? We could actually do that, to be honest. And based on this information or assumption, I'm going to go and look at the data. I'm going to try to make sense of this. Say, the reason why people in this weather station in Toronto in 2010, January 3rd, 2nd, whatever, they didn't mark the snow measurement for a lot of hours. And all of a sudden they marked it on the 4th day, okay? Saying that, oh, it snowed 1 centimeter in the last 6 hours. They put a measurement. So then it's safe to assume that it did not snow at all here. Now, if it didn't snow, now it might have rained. That's actually in the first column here. In fact, it did rain here in the last 6 hours, but no snow. No rain, no snow. No rain, no snow. So I'm gonna look at these two values for the missing hours. And I am guessing it's gonna be somewhere here. Well, it can't be because I know the temperatures are below 0 in Toronto here, definitely. But it's about relative humidity, that the relative humidity will be below 55. That even if we shift this graphic, you should see these green guys accumulate over here. Since we'll be real data wise below that 55, I'm guessing that's what's going to happen. Now, I can run calculators, or luckily the game is sort of working like a calculator. I'm going to set the date to the first day. This is sort of noon, like 11 o'clock, right, in the morning. Let's run the game. I'm already calculating relative humidity based on temperature and dew point. So these are real values. In fact, these values are the values that I'm here. For example, let's actually pull this here. What is the day here? Day 2, 9 o'clock. So let's go to day 2, sort of afternoon. So we should have -12, -13. We are there. We are quickly approaching day 3. Me finding the data is always slower than this guy running. So I'll go noon. So we should have 11.5 or 16. Yeah, there's rounding there. Okay. So humidity is calculated correctly. And actually high humidity. You would expect it to well, we are assuming it should snow, but there is no snow recorded. I bet there will be rain recorded. Yeah, so there is rain recorded. So we need to be careful about what kind of precipitation we are after. If only we could see the math behind this. Because this worked. For example, Temperature 1.6. Relative humidity. There's actually another calculator for that. This 0.6, 0.8. What are you doing? No, it's 94%. Plug that in here. Probability for any precipitation to be snow is about 30%. In fact, it's raining. So we need a good cutoff point. We need some smart equation there. Which brought us to this article or paper. But the 3 phases. I'm looking for that familiar graphic. I guess it was this one. There was another one where they marked the states. Or was it a web page? Water 3 phase. I think this is what I remember. Wow, that was a much more. Yeah, this is. So let's do some constraint check. This is kilopascal, so this is essentially 102,000 Pascal. So there you go, kPa. So most of the time, the weather people experience is going to be along this axis. Okay, this graph is presenting extreme pressure cases. So it's very unlikely for us to ever experience this part of the graph and also this part. So we are going to be in a narrow band here. Also, these degrees, according to the data we have, the minimum degree for us is close to 100 minus 100 Celsius. So left of this area is not relevant. This freezing point at 1 atmosphere is this dot, this crossed out section. Okay. That's like 0 degrees at this temperature, or Kelvin. Okay, 1 atmosphere, which is 1 bar. That's the ideal freezing situation. And you have 100 degrees to boiling. So as much as it looks complicated, if it's going to give more accurate results, I'm willing to implement the necessary parts of this versus this, because this never really tells me what's happening here. However, here I can make decisions like, well, it's this degree, whatever, -10. I'm here, right? So where am I in the pressure scale? I am somewhere over or under. Okay. Sometimes it will be liquid, sometimes it will be solid. The question is, this kind of looks logarithmic here. Let's say this is, yeah. Yeah, this is logarithmic, which this is looking a straight line because it's logarithmic. And I'll tell you why. Based on this, left of 0, right of 0. Left of 0, right of 0. Things drastically change, right? It could be rain quickly or snow. Ish, approximating. But as I keep saying, there is that we shouldn't make a blanket assessment here, or like assumption. Left of 0 is always solid. It looks like that here because we are losing the detail here. This vertical curve is essentially, this is a curve, this is not a line, right? So this line will be more pronounced here, the curvature, once you spread this distance out to nominal values instead of logarithmic values. Because you cannot just say half of these is like 60. You cannot just take the average of this. It doesn't scale. Because if it did, then you wouldn't have this distance the same, but comprising a different range of value. Here the difference is 9. Difference here is 90. So at each step you go 10 times more. So this, in essence, this line here is at each step is sort of 10%. I don't want to say zoomed, but you lose 90% of the detail. So then that curve is more pronounced here, but the same curve is looking more and more a straight line here. Interestingly enough, There's another missing link here. We cannot use this after all. This is, we cannot use this after all. Looks promising, but it's misleading. It's an isolated case where water is still. There is no dew temperature. It's based on pressure and temperature. Something instinctively here doesn't make sense because we are illustrate rain. Looking at this graph, temperatures like this, spring day, summer day, anywhere between this range here. It's as if it should always be raining, right? Around this pressure line. In fact, it's as if like there should never be water vapor. Like like all the vapor in the atmosphere should just be liquid according to this graph. And we know that is not the case. It doesn't rain all the time, right? And where would be ocean, there would be no atmosphere, that kind of thing. So this is ignoring the dynamics of water molecules in air, that kind of thing. This is like a lab case where you could adjust pressure. I'm sure this plays a role in real life, but things are probably shifted around. Cannot really take this. It's helpful. I'm just making up keywords. Similar idea. This is sort of a zoomed in thing. It excludes those higher and lower pressure values. Same idea. Spring, summer day, everything looks liquid. This is something we are already using. So we kind of need something like this, except parts of this graphic should show us, well, this is based on the assumption that it's displaying the type of snowflake, but yeah, something is missing. None of these pages so far. What can we do to incorporate this or these equations? Water in sky have low pressure? Good question. Water in sky will have lower pressure by logic. That's why I'm generalizing here. That's why planes want to go to higher altitudes to have less pressure, less air resistance, that kind of thing. So yeah, water molecules that are high in the sky will always have less pressure applied to them when, let's say, you have a glass of water, which has like the whole sky's worth of like pressure over it. So it's a low pressure system. Why graph? Because these are always isolated cases. These are sort of like lab conditions. But I'm just thinking of what you said. So if higher in the sky, are we coming down to these ranges? So let's ask ourselves this question: what is the pressure at a certain altitude, right? If at a certain altitude where clouds are, if the pressure is around here, then that will explain why things stay in vapor form, right? And maybe wind is pushing the clouds down, so they go to lower altitude, which is higher pressure. They tend to go in this area, then they precipitate, they go into liquid form, so you see them rain. And suddenly when the temperature drops, then you see the snow. So this may still work out, um, which is interesting because we do have cloud ceiling height. We could incorporate this, then it'll be absolutely crazy and fun at the same time. Pressure by altitude, air pressure at altitude calculator. Calculate air pressure at altitude. This is like default temperature. Let's say a kilometer. So this is like 90,000. This is 100,000 or 101,000. So okay, 1,000 meters. You might have brought up something that is that might be key, really. Because if the missing link here was that I was afraid everything was supposed to be liquid, but yeah, if a low pressure system is keeping it in vapor form, and that low pressure system could be the clouds. So now, at 1,000 meters, we are at 90,000. Problem with this graph is this is still logarithmic, but I see they actually put the lines here. So 90 is still going to be here. So it's not. However, 15 is going to be here. So liquids. So according to this, at this altitude, the clouds should start precipitating, or it should start raining. Let's go higher. Let's find some higher value in Toronto. Let's say it's 3,600. Actually, if we know that it's raining that day, there you go. 2,700. In fact, they recorded rain. This is quickly going down to 72. Temperature is where was it? Temperature is minus 10.7. Call it minus 11. It's slightly lower. Pressure at sea level, that is also 10,146. 10, 1, 4, 6. Okay, doesn't change much. So 70,000. 1, 2, 3, 4. So we are now a little bit here. Again, this has to be zoomed in to see. Oh, wait a second. I'm at -10. So I should be seeing solid. So technically, we could have snow here by sort of rough assumptions, right? I typed the temperature wrong. I'm not sure it's going to change much. It's supposed to be -6. I typed the dew temperature. It's going to be -6. Didn't change much. So assuming this graphic is too zoomed out, that if you were looking at this area more closely, maybe we would actually really see the difference between phases. So it's promising. Also, its sky temperature must be lower. Absolutely. I was actually just thinking about that. Because this is surface temperature. I'm thinking of the kind of end result here. I'm having a hard time visualizing the code too. I'm gonna try to work backwards from there. Because for a human mind, when we apply values here and we just look where it's supposed to fit, we make a determination. But how could you write the code here? Essentially, we need to get a true or false value. Is it snowing? Is it raining? That kind of thing. Or we get three possible results. It says snow, rain, or gas. That kind of. This cannot be done with basic if-else blocks, which is the whole point of this curve. You cannot just say if it's minus whatever. The code won't know anything about the graph or the equation. So as much as we are trying to make sense of it and say, you're right, like the temperature might be. Let's find another calculator for that. Temperature by altitude. This is a website I use a lot. This is feet. Yeah, that's the only downside is American units. Let's see, feet. Oh, there you go. The SI units done. So altitude, sea level around here, temperature is considerably less. So at surface, when it's 15 degrees, it almost drops down to half value, 1000, and like significantly low and goes below. Okay, here, wow, wow, okay. So sometimes they have equations. I need equations. Maybe we'll find the equation on another website. Here's the graph. Let's go Kelvin. This is meter. Good. Okay, this is 10,000 meters. We won't worry about that. But we won't worry about anything over 10,000. So this is good. The reason why I'm making that is because this looks like a linear function. I can figure that out based on these values. So are you a Godot fan or Roxa? Or hanging out for looking at the game progress? I think I'm seeing your name the first time. I might have forgotten. Sorry if I did that. So slowly writing code in my mind. Is this in relationship? When it's 15, it is this. It's to be. Oh, your nickname is different now. Okay. Odie. Yes. The cleaning guy. How is stuff going over there with the turmoil and the dynamics? You don't have to comment if you don't want to. Just go and I see girlfriend's account. Crazy shit going on everywhere, but especially in your part of the world these days. Looking at this, it kind of feels like it's the same temperature, but Kharkiv. I'm actually curious. I'm a fan of geography. Oh wow. Okay. Yeah, you're close to the border. Cool. Well, depending on what it is, of course. Like I mean, sometimes it's not so good to be so close to, say, potential danger. Fifteen at 0. What is 15 Celsius in Kelvin? Let's do Fahrenheit to Celsius, and then here we'll change this to Kelvin. 288. Kind of should have known that actually it's this. 288, which is here. I'm thinking this is sort of a source of truth, right? So this doesn't care for real weather conditions. It assumes that under perfect conditions at sea level 0, temperature should be 15 degrees. But in reality, let's say we are at -6. So there's 21 degrees difference. So then whatever we calculate, I compensate for that. So we are doing something like this, minus, no, 2. Let's assume this is 3000. So then this should be 21 less. So let's say minus 25. I'm really pushing things here, but so it's 66,000. And it here. So this first line is 20, then 30. So we are sort of really kind of in the middle. And let's not forget that this new temperature is minus 25. Let's pull this here. So we are somewhere here. Is this logarithmic? No, this is real. Okay, 25. So along this axis or line, altitude 3. We don't care about altitude. It's the, oh, sorry, we did this 66,000. So it should snow. And yet it's raining. Or it has rained 10 millimeters in the last 6 hours. But it did rain. And the temperature difference is negligible. It's not like it's from plus 13 to minus 6. The cloud height is around 1,000 to 3,000. So plugging in the values when we know it's raining, the result that the interpretation we are getting to is snow. I'm gonna reverse things a little bit. Let's find a case where we know it snowed. And it snowed for sure, not like this bullshit case. It actually snowed twice as much since the previously known snowy hour, right? It's 2 centimeters of snow. 6 hours. So what are the conditions? The cloud height, by the way, this is actually not the real cloud height. This is the lowest visible cloud height. So this is not a proper value in retrospect. So the snow forming cloud could be way higher than this. So there's still that possibility. We will maybe make a blanket assumption. Fuck it, it's 10,000 meters. Okay. Now we might be getting somewhere. Okay. Now, based on altitude, this 10,000. What was this madness? 10,000. Okay. This is minus 50. So, but then I'm mixing things up again there. Because by keeping this static, I'm always keeping this static, whether it's the right value right now or not. What's the degree? 15 minus 5, so 20. So this is going to be 70. It's going to be even lower, 13,000, which is going to be, this is 20,000, so somewhere there. So clearly it's snow. Okay, this checks out. Now, keep this logic. That's the problem. Keep that. Go to another hour where we know it's raining. And there's this weird case that it's raining and snowing at the same time. Let's ignore that. Minus 10. So it's supposed to be now 25 as difference. So this is 75. 12,000, which makes it even. It's making it worse. Because see what I can deduce from here. I'm going to introduce relative humidity column here. Insert RH. Let's look up that relative humidity formula. Weather system. This is this. We could ignore the 100 part, so it's exponential. Take the whole thing. Speaking of which, that is in fact this could very well be Excel formula, XP. We'll swap the TD with the cell and the T with another cell. Stick this in here. Let's say it's this. Is it XP? It is. So the TD is U, which is G2, right? And the T is F2. So let's skip this part. The fuck is your problem? Okay. Why is there what the? So this is that, right? So this bracket could just be one expression. That's fine. This is just one number. Here's another number. So a number over a number. Exponential. Okay, exponential some number over another exponential. Some number over some number. Do that. Take the exponential over some other exponential. So okay, what is the problem, sir? Error in value. No fucking kidding. What is the error though? There is something with the way your formula is typed. Oh. Because in my mind, these are numbers. I should be getting the 1.6 from here. This is a string. So, duh. I'm already calculating the real values here. So that checks out. Yeah, that is my mistake. I'm gonna create 2 more things here because there's no shame in doing that. So we'll do this as T and this one is TD. Okay. T is this cell, but we gotta split. Split I think works, right? Right? Wasn't a split? replace alt text start num just there is wasn't replace was in Google Docs. This one is using substitute. Alt text, alt text, new text. What is the text? The text is F2. Alt text is anytime you see I'm assuming everything is 1. Here's the new text. Just do it. And then you take the value of this, so you convert it to a numerical value. And then, if possible, divide that by 10. Smarten up. Okay. So you do this. I want to see. In fact, copy this. Go all the way, not like all the way down, but just enough. Let's okay. There. So okay, +8. This is good. We have some cold days in the middle of December. This is fine. We have -10. This is fine. Then do the same thing for G2. Right? Find it. And then just do it. Here you're freaking out because you have 9 or something, and I honestly don't care about that. Actually, I should. Oh, this is when I was fixing my data lines. However, the FM16 ones will be ignored. This will actually be taken out anyway, so that's fine. So we'll ignore that. So now this is I and J. FG has become I and J. So this is now J. And this is now I. If I say so myself. Oh. And also smarten up. Multiply this by 100. Copy. No. Okay, can I see a pattern between this, this, and this? And also, well, this ish. Maybe I'll make more sense out of this than one thing I'm noticing. The T values are relatively the same, right? Something that I'm seeing here, RH values are dropping. When they are high, we have rain. And here's a case where they didn't record rain. The relative humidity is high too, but then this is slightly lower. Then when 1 is like from 0.6 we go up to 1 again. This time RH is dropping. which is sort of saying, well, then there is not enough humidity to rain. So then it's either T is low or RH is low. You don't have rain. Temperatures are dropping, but relative humidity is also more or less the same. There is no rain. Go down. Then all of a sudden we have rain. Remember that this rain is recorded in the last 6 hours. It doesn't necessarily mean at this hour, because of this, it is raining. And because the data is so fucked up, this 6 hours could have actually, like, it could have rained in these first 2 hours, then no rain. Which makes much more sense in my mind, which brings me to another point. If I'm going to distribute this value to the previous 6 hours, these 2 hours should probably get most of the rain because there's more likelihood of rain here. And not that much rain here. Interesting. This is slowly going in that direction that one of the viewers yesterday mentioned. You might have to use a statistical analysis software like R or Pandas, one of those fun things, to fill in missing data, which then turns into a whole other project. And again, relatively low humidity, no rain. So 85 is still not enough for rain. No rain, no rain. Come down. It's consistent. I'm seeing a pattern here. Normally 85 wasn't enough for rain somewhere here, or it's sort of the threshold, right? It's low temperature. This is 85. Maybe it rained mostly here. It rained and a little bit snow. And by the way, as far as units go, this is 1 centimeter. This is 5 millimeter. That's how they did it. So this is still not that much rain. Half a centimeter rain. Not bad, but if we see 50 here, it's like some rain. Like it's shit show. And then we have snow. Pressure. Relatively low temperature. Humidity is still high enough. Rays rain. I think 160s have snow again. Rain 0. There you go. The 86, 85 thresholds. There's something interesting regardless of this. Here it is, more snow, more rain. Temperatures have risen, but relative humidity is even higher than this. Let's look at the pressure, which is high enough. And then the magical 85 threshold. There's some decimals here. 85, and suddenly no rain, no snow. Let's look at this 85 in light of this. 85. If I were to assume that below 0, this is no longer going to be a triangle, but you will have that's what I think it should happen. You would have these values sort of accumulate here. I would expect to see nothing here. So this is more like a shape like this. So there is this 85, which is 9085 here. So it's a way of simplifying it. Yeah, look at that 85. It's like magical. It's like nothing is happening. Nothing is happening. And then there's rain and snow. This is a fluke. This is really low-ish. Okay. Let's go to the end of the year where we could have maybe more snow. Let's see. We are looking at P, I believe. We are still in December. Some snow. That's a mistake. Okay, this is one. This is the wrong one. Magical 85. Two 2010 was a weird year. We didn't really have that much going on snow-wise. Let's look at the rain. We usually have rain in May and August. Here's August. Yeah, something like this. No kidding. Yeah. When dew point is the same as this, it's 100% humidity. It just rains. It's like there's zero chance for not rain. I'm gonna grab a glass of water, and I think I will tackle this with some basic if-else case, something like if it's over 85, it's going to precipitate. We don't know whether it's rain or snow. Then as a sub case, I have to incorporate a few more cases where, well, okay, over 85, some shit has to happen, but what kind of shit will happen? Is it rain? Is it snow? That's the decision making. And I have yet to see a case where below 85 anything happens. If that happens, then I have to start thinking more. But I think I have thought long enough. Uh, Water first and bit of implementation. Let's do a spot check. Snow, still 85. Sorry, I said snow, but rain. Check. Go to May. We have a lot of rain in May too. This is a fluke case. But I think the 85 is going to stand for now. Find a rainy day. Maybe we could also ignore the 5mm ones. But they will consider them insignificant. Especially if it's spread over 6 hours, it's going to be insignificant. Okay? Because 6 and 30 is every hour is 5mm. When it's just 5 over 6 hours, it's like basically what? Less than 1mm per hour? It's really insignificant. It's like if you spit, there's probably more accumulation. Yeah, like say insignificant, this is already 71, so we'll ignore it. Maybe we'll even pull the threshold down to 80. Once we have something that looks natural, as far as, well, that time of the year it's supposed to rain or snow, then we can maybe fine tune it. So there is an old is raining function here, which is looking up must rain, which is sort of awkward, like the story is set to a certain value. I bet this value was changed with the click of a button, but we'll now. We'll just tie it to real data. If I change this, the existing systems might freak out because they are. Well, it doesn't matter because this is still returning true or false. So, according to the weather data, we could do something like this: get relative humidity, right? However, the logic that I'm Planning to write down maybe is not supposed to be in Godot. Let's open VS Code. There was something in the expander in the cleanup functions. This is the snow part, and this is the rain part. As much as I don't like to do it, I may have to change my macro to do this sort of cleanup. So then I can there's a lot of work that is done here in the expander, which is relying on cleaner functions. And this is each one of these cleaner functions is part of loop. So when the cleanup is done, in a sense, we are parsing all the rows, and these are the cleaner. The columns become like cleaner functions. So then we are processing each cell. This one has one comma separated value. This one has multiple commas, that kind of thing. So we try to extract the meaningful part. In the wind case, we have wind direction and speed. Here, the fourth number is the speed. So far that actually has worked for the basic 6 types. And then there's some data, some like attempt to clean up missing data when it's nines. You look up the previously known healthy value. This to a certain extent works, but then you get to cases like missing values like this, which is hard to fill in Node.js. As much as you want to go back and fill in the details in a for loop, you have already skipped the previous records. To determine the value of this cell, you can still do forward and backward lookup. It still skews things, to be honest. If things are fixed here and Node.js is kind of transforming these values to something more like this, which is necessary for the compression later, then I think that might be a much better exercise. Basically, the Node.js layer has to be as dumb as possible. There's a lot of business logic here. So when the data is missing or corrupted, there's only so much you can do. And let's not forget that this is only this year for Toronto, and in other files there are different horror stories, which means if you don't do the cleanup before we trigger the Node.js, you will have to write more and more exceptions at Node.js level. Maybe that's less than ideal. So it is now time to revisit our good old friend, this guy. So first we rename the sheet to sheet 1. We get rid of redundant columns. I'm actually going to reopen this so that you can follow what I'm doing. This file. Okay. I'm gonna try to put this like this. Yeah. So there is a lot of garbage columns here, like this is the call sign of the weather station, the quality code, that kind of thing. We don't want those things. So we select those columns, we delete them. Okay. And you're only left with the normal chunks. By the way, I just deleted my useful functions there. But anyway, then what we should do is then what I'm doing right now is that I add another sheet before this one, and remember this has been relabeled as sheet 1, and that new sheet is now renamed to without FM16 because we are also getting rid of the columns. We are about to get rid of the rows where the column for the report type is FM16. Okay, we don't want those. Then we don't want to display the zeros because for missing sections it automatically fills the cells with 0. We don't want that, so that's set to false. Then we in the new sheet, because we have fewer rows and columns, we have to calculate the new values. And then in the new sheet, the first row and column, this A1, it automatically is selected, but essentially we paste the formula there. This is where we filter out the FM16 ones. So it takes a copy of this without this. Then we save it as macroscopic TSV. Now, before we do this, let's ask ourselves this question. So the reason why this is working is because when I was manually doing this process, I understood that the column letter for comparing FM16 happened to be let me see. If A is gone, C is gone, D is gone, that's 3. E is gone, 4, 5, 6. So there's only B left, right? A, B, C, D, E, F, G. So then H is becoming the new B. Yeah, that's it. This is the new notation. So instead of checking the B column, if it is 16, this one is basically saying out of all the columns, the first index column is essentially B. If we said 0, this would have been the new A. Okay. That's fine. Because I'm going to have to do something here. I'm going to have to introduce a new formula. Imagine I manually removed all this. At some point, it felt much more comfortable to write JavaScript than this. That's why I'm still debating whether I'm doing this in the macro or not. Because in a way, I'm already parsing this. This is splitting it, so we take the pressure, will be output. We even do a lot more, like where is the tendency? Is it going down or up? We compare it to the next value. So for a record, when I'm in AL1 or AA1, say this is rain, okay? for this record, I have access to PMP and dew. So I could easily calculate the relative humidity. So I think I could still recover from this point. Still keeping things in Node. First of all, let's do this case. AA1. Is it raining or not? But that's still half of the equation. Let's say in this world it is not raining at all. We only care for snow. So this logic that I'm going to talk about will be extended to the rain logic or decision. Let's just care for snow. So for AL1, we are here. For the first record, after of course the cleanup is done, and we could actually trigger the cleanup right now. We haven't written a single line of macro code. The old one is still working, so run it, no, and okay. So this is the list without FM16. Everything is a little bit tidied up, okay. So we don't have those missing 999 values, this is looking a lot healthier. We have trouble with this part. Node.js code is parsing this part. Okay. For the first record, there is no AL1. They did not bother to write zero snow. So from, let's say the machine doesn't know, right? The AI, the code won't know whether it is real zero or people ignore to type zero. So there is no record. So we were trying to determine snow in a primitive way, and that's the essence of today's struggle. So now, in determine snow, we have to write this function differently. Previously, we were looking forward to find the existing AL1 record and then dividing things and such. We will now do something else. Yeah, I'm just going to cut this crap and I'll say this kind of recursive function yields insignificant or meaningless values. So look up whatever is up here. I'm gonna write another function here. I'm going to keep it similar to Godot. For a certain record, this has to return an exponential function, which is here. This is going to be some kind of I am making some progress, yes. So I looked at data, found some pattern. So I'm assuming 85% relative humidity is sort of the good ratio. And I'm going to introduce some temperature variation in the main if block if we are over or under 85% humidity. We did look up with the help of another viewer today. The temperature at higher altitudes is lower, and the pressure is also of course, is lower. This had some relationship with the way these equations or these calculations are done. But this proved to be too complicated. And so I'm kind of like, I'm agreeing with you. I agree with you yesterday too. This has to be completed. I agree with you. It's just there was no sane way of completing that data in my mind. So I'm basically determining with the 85% holy, sort of this magical 85% relative humidity, whether there should be snow or not. If there, so this is kind of what I came to. When we see the next snow value, where it says this, right? After I write my logic, in most of these cases, we will get false. Only here we will get true, in my opinion. And then if that's the case, it's okay to spread out this snow value to these last hours. That's a bigger victory than using this as like some truth for all the missing values here. Because here it's really missing. It's not 0. But we'll just set it to 0 instead of some infinitesimal value. So that's kind of what I'm working on right now. So I'm calculating the relative humidity for this particular case, which is this formula. Where is it? This. We'll just put it here. There is no such thing as exponential in JavaScript. It's math E, right? Yes. And now you say math power. So you take e to the power something. Let the craziness ensue. So let's do this in 2 steps so I keep my sanity. This TD stands for do. Call it do exponential. Where I grow more gray hair. Right. Seems to be happening by the minute these days. TD. This TD is going to be some other shit. And this is going to be temp exponential. This is the temperature exponential, which is this. Then the way they did was do exponential was divided over temp exponential. This is the right way. So e to the power of this division, e to the power of this division, then those exponentials are divided times this is going to return the relative humidity. Seems to be a logistic regression, not based on my data. It's as if you're about to type something else, because if I consider your last sentence as a standalone statement, it is based on my data. What do you mean it's not based on my data? So based on the air temperature and dew, or in essence relative humidity, um, we are going to determine whether there should be a value here or not. If there should be a value, then like in most of these cases, I'm hoping to find false, so there should not be any snow. And when there is snow, that's going to be saying true for these values. If it's true, then for its value, I'm going to determine it based on the closest known date. Coefficient I'm using from another sample. Coefficient I'm using what other sample? Let me finish this one. PD is going to be the dew. I need to get the records. What did I type for the dew? I think I might have just typed the dew record dot. Yeah, record dew. I need to access the part here though. Coefficients. But something doesn't make sense in like what you are saying doesn't make sense. Like another sample, like this is the only file. Like I'm not sampling from a different file. Like I'm not sure. Come up with the equations. You have to compute the coefficients. 17.625. A sample. Okay, but I don't think I'm working with equations at this point. So this is turning into so imagine I want to type a value here, just true or false. I have to make a decision based on some of these values. So that's all I care for right now. If it's just true or false, then there is going to be another step. So I'm not really dealing with coefficients or equations at this point. The numbers in my equation, I think you're referring to this one. This one. Nope, sorry, this one. This is dew, this is air temperature. In my equation are based on some sample. No, this TD and T are literally this. I'm just reading it. For this to be determined, I'm looking at this and this. For the second rows AL1, I'm looking at that relevant rows dew and TMP. So it's sort of like every row is determining whether this is true or false. So I'm not really sure there's like there's only one equation. I'm not really coming up with more equations than necessary. Not the parameters, the coefficients. No. let me finish what I'm doing. Maybe it'll make sense to you. I'm not really getting what you're saying. Like, if you're talking about what I'm doing, I think I'm on the right track. If you're talking about something else, I'm not understanding what you're talking about. There's a bit of disconnect between what I'm seeing on the screen and what I'm making sense. I I think, yeah, you are maybe thinking in terms of statistical analysis and all that stuff. If possible, I don't want to get in there. However, I think you are pointing out something else that I'm missing, which I noticed, but let me see. Nope, the values are correct. So I still going to continue this. Let me see where this is going. Okay. So when I get the records view, which is like this, um, records index is actually that. I'm kind of doing this, but because I'm already in there, I don't really have access to the calculated data, do I? I don't. So in a sense, I'll still do this. This, though, is going to be the split here. So let's do something like this. Var temp. Temperature is the records due. This. However, due cannot be like that. It is going to be split by this. You take the 0. Gotcha. And then copy paste. Then let's keep this in order. View. Then this should be TMP. This is good. This temp has to be this temp. And then the rest has to be okay. Now, get RH of current records, which is this. If this is more bigger than maybe equal to, we don't know. That's what we are deciding. Let's say you return true. And true in our case is I'm just hard coding it like this. Else return to 0. Let's just go with this for now to see what's going. You have two equations with terms TD and T. Yes, they have just been fixed, and your message is from 3 minutes ago. I think everything is checked out now. So the current records temperature and due will be factored in here. I want to double check that I'm dividing the due by temp. I do. This is due, this is temp. Okay, moving on. Determine snow. Now, when the record doesn't exist, we pretend it exists. Well, no, actually we don't. Well, I have to change something here too now. Because I was trying to fix the record by slapping some value here. And which led to this sort of madness here. What is it here? Which is then split here again. We cannot really do this anymore. What we should do is we kind of have to return this anyway. So I'm going to do a premature return here. Let's be careful. Premature return for the sake of sake. Okay. Record AL1 is going to be okay. No. I'm approaching this from a different point of view. If the record exists, what will happen? The record exists, which is this. If it's 99, fuck it, it's 0. If it's not, then do depth duration. So none of this will be true. I have to incorporate this later. Okay, this is where we'll do something like this for the moment. This snow has to be normalized. However, because I'm hard coding it to 1000, it's already normalized, so that's done. If it's not, then if it's fucked up, fix it. Then this will get normalized anyway. This is based on the false previous times logic. This is no longer valid. Snow is supposed to be just the depth. Then that, yeah, this doesn't have to be thresholded. This is about quality check, which we ignored here because of this assumption. This may have to be retriggered. This is a different kind of check. So if the depth is calculated, it will be normalized. Put here. Okay. So in the final situation, we will do. We have to go in expander. Not necessarily here, but I want to see the path. Resources, data, geography matters, climate data. Then I have to do this. Cannot access snow before initialization. Cleaners AL1, line 11. Oh, what is snow? Stum of me. This equals record. Record is missing. Determine it. slap it. That's done. So this is now going to give us a different result here. AL1 happens to be the last one. Okay, so like before, we should see pretty much the first 50 or so 0. Or 1, if I reverse the case. Did I? At least it's doing something that I where is it? Yeah, so it thinks it's more than 85. Let's see if that is the case. Well, when I stupidly deleted the calculation here, I can't remember which date had low humidity. Somewhere here, but they could have been the lines that we are removing from. Okay, I'll do it again. So this is going to be exponential, this formula. Dew over temperature. I'm going to move this one up, this one up. Okay, easy to follow this. Dew, G2. Okay, so we'll do substitute. Substitute. Thank you. G2. We assume it's always comma 1 with empty text. Then you take the value of that thing, divide it by 10. This is u. You multiply it by this. It just gave us this over. This has to be kept like this. Something similar. This is still the dew. This number is different. I wrote these substitutes in a different cell before. This is the top part. This altogether has to be divided over something similar, but the column letters will be different. So this whole exponential has to be divided over this exponential, where g has to be replaced with f. So on the typo, do you accept the correction? Where exactly are you correcting me? How will I know? How do I know where you're correcting me? It's difficult to read. I might have to do the, I think there has to be, more brackets here. I forgot that. Do that, which is clearly wrong. So, okay. I'm going the proper substitution here. The first, this one is the temperature. Oh, it divided the wrong thing over the other one anyway. Okay, maybe yeah, this is this to be reversed. Right? Dude. Fuck it, I'm doing the proper way. Value is the value. I'm gonna put it here. 1.6, perfect. Do the same shit for this. You should not be that, you should be G2. Good. We'll take you all the way to the bottom. Then the J2 times that. Again, J2 times this. I see the brackets are in the wrong place. Most definitely. Okay. Take this. This over I2. I did this like half an hour ago. What am I missing here? E to the oh, it's plus, not times. Something was clearly overstated. Okay, there you go. It's 94% humidity. Copy this. Missing the fucked up values are fine because they are for the rows that are supposed to be removed. So for most of these records, we have AL1 1 is good. This one should give 0. How will we know what this one is record wise? It's 11 o'clock. This is record probably 12 or 11 based on removing this header. 11, so I guess right. Okay. And after that we have one more 0, which checks out because this is still 0 0. So we will have 3 zeros followed by 1. 0 0 0. 14 should be 1. Good. So this shit is working. So according to this new logic, based on relative humidity, we say, well, it's a very raw logic, but well, if humidity is more than 85, it should snow. Now we have to introduce other aspects of this, such as is it below a certain threshold, which is this idea in a sense. Because we cannot assume that it's always going to snow if the humidity is over 85. In fact, over 85 and 1 or 2 degrees, we have the rain sort of coming in here. That sort of thing. I think what is going to happen right now is that I have lunch, and then I punch more numbers. So lunch and punch. So I'll see you after the break. Okay. So we have good cases here. Let's get back to the 85 threshold conundrum. So we have confirmation that for these three values, we had 0 output, and anything over 85, we had 1 output. Now, of course, that's such a rough approximation, so we have to fine tune it. We are not accounting for temperature, and that's what we should be doing here. Music there. Okay, let's get back to the equation or the chart. The graph we are using. So for over 85, we now have to assume that this is the norm outline. So we'll consider it. Let's take the average. Let's say 2 degrees. If it's over 85, but less than 2. Actually, let's exaggerate it. Less than 1. Do that. Let's say, and what's the temperature? The temperature is that records we don't have utility functions here to extract the exact value of something like a measurement we want. Get measurement for is a function we wrote in Godot. We don't have that yet here. We may never have. So this records index is going to give us the temperature. So if this is less than 1, then it should snow. That being said, even though we had ones here and then 0 and then 1 again, right? This is 0 because originally we said they are less than 85, so they are still going to be 0. What is it? Okay, when we had ones here, we assume it should snow, but then we are deciding no, it shouldn't snow because the temperature is not less than. Then these will also be 0, which is good. So we are bringing these wrongly marked or incorrectly marked cases back to sort of the healthy values. So when we run this and we refresh this, these the first 10, which were 1 here in the 14th index, they should all be 0 too. And in fact, I see them 0. Okay, 0. This was already 0. This 3, the original 3, 0, and this was also 1. This may actually be 1. I haven't checked that record-wise. In fact, it's over 85 and temperature is here. So here it should snow, according to our logic. Now, according to the historical records, it doesn't. We may have to fudge those thresholds now. It's kind of what we'll do. Maybe 85 is, I don't know, maybe it should be 88. Something like that. Which will make all these cases true or correct. Here we'll have some weird things. So it's over 88, and this is also favorable too. So it should snow here. However, we don't really have something. So my expectation is that I'm going to mark all these 0 until I get to a value that is near here. Disappear, we will have snow. How do we know the value of this? January 1st, 20 o'clock. Should be 20 in the index. Let's make this 88. Yeah. Ooh. 19 and 20. Did I miss something here? 19. It should be. No, they're okay. Yeah. Wow. Logic wise, they're okay. Yeah, I was not. Problem is, what is the value of snow depth? I also code another 1 when I refresh the data. I think somewhere 7th or 8th. Yeah, this one. 7th is the 6th index here. Which is this? Yeah, this is 100. But actually, that's not correct. You'll be looking at 8 here. So it passed this test. Oh, of course it passed this test too. Let's incorporate a third factor. Let's consider pressure. Record-wise, for the fact that they ignore to mark it here, we are assuming there is no snow. So we are combining a bunch of these values to give us a Boolean value. And we represent those Boolean values by, yes, it should snow or it should not snow. So far, the assumption is that the relative humidity is really high and we are at low enough temperatures, it should snow. However, some of these record-wise here, it clearly shows there is no snow. So this condition isn't enough by itself. We have to introduce a third factor which would push some of these cases to the else block so that it would satisfy the this result. So we are kind of mapping the reality to functions. So let's go down, and I think around 60. Nope, I'm wrong. Here, around 75, we have a little bit of snow. Let's look at the pressure. So it's 10, 1. Write some stuff down. For that, normally need pencils. So let's smarten up. Some help. So record 75. Pressure is 10, 1, 4, 2. We have some snow. I'm also going to mark the temperature, which is minus 10.3, and the dew is minus 12.7. Okay, and relative humidity is 82.5. Now we are way over. Wait. Oh. Something else occurred to me. According to our logic, if we had to determine whether it snowed at this hour, our code would say no, it wouldn't snow. The fact that this is here is actually, this means something else. This is showing that it snowed in the past 6 hours. Doesn't necessarily mean they are counting this hour. This hour's snow accumulation will be calculated in the, or will be announced in the next record. But then I still think it doesn't snow here. It's because this is here doesn't mean it should snow. So which is okay because we'll assume this 0. And if in fact, if this deserves to have snow, it will be determined from here. Okay, something checks out. Which means if it's not going to be here, so let me, 75 is still kind of valid because it's a good marker here. So in the previous 6 hours here, out of these 6 hours, because we said this hour's measurement will be marked here, because this will be the 3, 6 marked here. So this is going to be, this is showing this interval. Out of these 6 hours, I would expect this to be the snowy hour. So I'm going to fix this back to 85, okay? Because we are factoring in other stuff. So the relative humidity check. Um, Temperature is less than this, check. Okay. This is still not a good example for me to factor in the third part. I'm looking for cases when I know for a fact that, like, maybe I'll introduce an OR case here, right? So let's look here. It can't snow, it can't snow, it can't snow, but it did snow. So out of all these 6 records, this is the hour when it's making much more sense for snow to, which is close to 85. So I could lower my threshold to 84. Let's just do that until I find something else. Clearly snow. This checks out. So no snow, no snow, some snow. Some snow, definitely. Go down here. Here's 6 hours. No snow, yes, yes, definitely. This is a 99 case. What are we doing for that? If it's, yeah, we assume it's always 0. I think this is kind of working, but I have to check. Will automatically, well, it's gonna be 0 for the fact that this is actually less. Here's the problem case. Actually, I'm seeing it right now. It's more than 85, but the temperature is less than 1. So it will actually want to snow. So we have to exclude this case. So this is when I'm going to introduce maybe the pressure. So if it's less than 10,100, there was some number there, 10,156 or 36 something. There's a default value. 6 or this. Yeah, I manually typed this in, so let me check. Yeah, 325, which is going to be this off, so 132. If it's less than this, then still mark it 0. But here, Did snow. So say it would have snowed here. Makes it weird because then this is not, well, we could put a strict sign here. So then it'll be exactly 1, 2. Okay. But if I put an end case and I say okay, what do I want to do? Put an end sign or end clause and say less than some threshold or higher than. Let me see. What did I decide here? It was high. It would pass here. It would pass here, but we want it to fail here. Where can you find the data? The data is it's this. I'll give you the CSV Toronto case too. So it's 7166. No, wrong. 71624. This is the one. This is Toronto. That same file that I will. Down the rabbit hole. Good luck. There's a PDF file to make sense of the field names. I don't think you'll need it, but if you need to know, let me know. I'll pass along the PDF file. It's hundreds of pages, but you could find the relevant chunks of these IDs here at the top in the header. It's a horrible CSV format. Like it's not, there's CSV of CSV. Some fields are all already there on, like they have CSV values in some fields. It's kind of weird. Okay, where was I? I said there is a high humidity case, low temperature. We assume it's not snowing. So how do we exclude this case? Because otherwise this will pass. We say let's make a blanket statement. Again, if it's more than 10,000, let's write some of these fields like this. Turn record records TMP, just like that. And you say still need this, but now you can do something like this. It's let me see, RV multiple, oh, it's 10,000, I see. Then we'll do something like this. Get pressure. I think they called it SLP, sea level pressure, so I'll In fact, it's just like that, but without this. It could be parse int. I believe that's what I'm doing in here. Kept it like that. So let's go here. Record number, it's 6 here, it should be 8 here, right? This is passing because, well, first of all, RH is high and this is less than 1. But, well, since that's, oh, I guess see. Yeah, I'll give you the PDF too. So the PDF is let me see, doc. It's here. So if you go sort of up and down into the doc folder, but I'll paste you the folder. There's a ISD format document. I think this is the one that I use. That's yeah, this is the one. See, this has all the fields. So it says it for the records way down here. I thought the greater than should be used, but now I'm thinking it should be less than. Just sort of contradictory because if I check against this case, it should be less than, but then the below case indicated that I should use the greater than symbol. Okay, yeah, cool. So anything else, let me know. Save this, resave it. Let's run it again. Let's refresh it. I see a lot of zeros. Kind of refreshing. This is still 0. So essentially, I should be seeing 0 all the way down to somewhere here. So 71 should say 1, and everything else before that should be 0. Now, yes, I'm gonna do spot check here. $70, $71, $72, $3. What the? Oh, it actually found the, okay. Okay, it did this. Okay, that's fine. So this is where I hoped there would be snow, but it said there is no snow. First of all, it said it's over 85 or 84. Let's check. Then the temperature is less than 1. That's good too. Then sea level pressure 10,136 is I was hoping to get here one. One of these should be one according to this index. Let me see. This is okay, 73, because that 73 corresponds to 75. So then this 73 will correspond to 71 in the records. Good, good. No, it should fail here. Actually, the code should fail. The code is working fine. But it should have marked it as 1, not 0. So I cannot really base it on pressure, because if I'm expecting it to snow here, then I'll have to mark this over some number. If I do so, and I go here, it should snow here too, and yet they didn't mark it. Independent variables. So I'm guessing you're writing remark 2. Because you kind of pasted the same remark, but I'm just making sure. In case you're hearing me, but you're not seeing your screen. Well, that's kind of the goal, but I don't really know how to clean it, to be honest. Like, this is my goal to clean, or my attempt to clean. Sort of making decisions. I don't honestly have that much statistical analysis, like that kind of software knowledge to write stuff to clean it. And yeah, the data is so in such a messy way that like everything here worked like a charm. Like I wrote everything that I'm doing so far, I've done it for the existing values and it works just fine. It's this fucked up cases. Then we have to make assumptions, generalizations, that sort of thing. Um, Honestly, the decision that I'm making, someone has to make those decisions in a different kind of software too. So they have to fill these values with either zeros or some values. So essentially, it's the same thing. I don't really see like it has to be cleaned somewhere anyway, but I don't have the capability to do that somewhere else. So I'm kind of cleaning it or making sense of the data when I'm extracting it or making it game compatible. That's essentially really the problem. I wish it had been like this. This is uh, this is workable. Here's another problem that I'll point out to you. I'll show you a file from Istanbul. It's a whole other story. Uh, let's pick again 2010. Opening. Those guys, instead of measuring every hour, by the way, there are 2 hours in Toronto that are in between clocks. But in Istanbul, it's a whole other story. So they've made the first measurement at midnight. Then the next measurement is 20 past midnight. Then they do it every half an hour. So it's non-standard. The half an hour business is the same, but they also measure every 3 hours anyway. This, there's this. Then in between those 3 hours, there's the 20 past, and then they're repeating 30 minutes. So it's inconsistent anyway. And then those guys didn't mark the AL1 properly either. So you come all the way down to January 20, and they said in the last 6 hours it's zero anyway. So then was it not zero here? Why did you have to emphasize it was zero? So this is at least what I would have expected in Toronto to be marked zero. Because, we are a snow taking city. Istanbul is not most of the time. And the next snow day is again in January 23rd, which is zero with the 99 error marker there. This is the same problem. So snow is a mess. So the accuracy is an interesting question. I would honestly value consistency over accuracy right now. Meaning, as long as I don't see snow in July in Toronto, it doesn't have to be that accurate, whether it snows in the morning or in the evening. The hours could shift. It doesn't have to be that accurate, but it has to be consistent with the month, generally speaking. Yeah. So if there is going to be a system, whether it's in Excel or Node, that is going to fill in values here, it should fill in so that we don't see snow in weird months of the year. That's the kind of consistency I'm looking for. Because honestly, if someone wanted to clean up this data, let's say this is a separate exercise. Say we are not building a game. Um, Someone wanted to clean up the data or fill in the missing values, saying that, well, should we fill all this with zeros or how much value? I don't know, based on some decision. Um, I'm kind of curious to know that decision, so I can maybe do it by myself. Well, the threshold is right now, according to this, it's still making some sense that there is something here. This is somewhat working. I have to fine tune it. There's something about this. This is a similar graphic that I saw in one of the papers you sent me yesterday. Um, so there was that 85% relative humidity coming up over and over again. Like this case, for example, there's this calculator. We couldn't. Yesterday, there was no way to reverse engineer this, but let's look at this calculator. Relative humidity is really high, but the temperature is over 1.6, so there's 30% chance of snow. So let's do 0.1 down. So even going 0.1 down is increasing the precipitation chance 10% by 10%. Let's go down one more. So that's there is something about the temperature and relative humidity, hence this code. I think this is proving to be useless, actually even incorrect. So see, that was interesting. Between 1.3 and 1.4, this didn't change. So it's not. Oops, I should have typed this. And below 1, I think we might even get 100%. It will snow. Yeah, it could. Oops, sorry. This is what I meant. Between this and this, there is no difference. It's 80%. But I bet if I type this, so maybe from here we can do some regression. Yeah, it is going to be about these two. That's clear. And then maybe based on this, I'll say like, yeah, if this is more than some number, I'll say, okay, it snows. So maybe I need a function that takes in this and this. It gives me a probability. If that is below a threshold, then I decide. How am I going to figure this one out? This might be more of your domain, actually. I'm kind of confident that if we figure this equation out, it might work on my data. You are claiming maybe not. But I'd rather have access to this, try and see that it fails, than not knowing if it might work. In a sense, I'm trying to write an equation based on the data that I have, but this is probably as close as I will get. I mean, in a sense, it is going to be some kind of fine-tuning like this too. You know what I'm actually really looking for is something like this. Where was that? In scripts. It's about it's for the weather evaporation. Shift P. I'm probably looking for the wrong file. Let me evaporation. There you go. So look at this monstrosity. This is only a small portion. There are helper functions like this, which is converting temperatures to Kelvin. But essentially, you plug in some values, and this is calculating the evaporation or the decay rate. And the visually it looks like this. This evaporation graph is this, but this Q is this, which is expanded. This is just the HS part. This PW, you have to calculate it based on this. So there are a series of equations. So I would be okay with writing equations like that. And I think this is the closest thing I can get to determining an equation. Calculate this. And this is the breakdown of this article or the calculator. So they actually said they are calculating the snow melt temperature. So they are kind of reversing it, thinking if snow is going to melt at the temperature, just below the temperature, it will also freeze. So then they are using that logic to say, well, then under these conditions, it's just about the melt or snow. So then they are kind of over the edge or sort of like under that edge of like melt, snow, freeze. And it's this graphic. So below the red line, we have snow. Here it's sort of rain snow mix. And if you go here, it's mostly rain. So humidity plays a factor, plays a role. Below a certain level of humidity, you don't have rain. And you don't have snow either. So it's not entirely a linear function here. And we actually saw that here. Taking this down 0.1 is not always giving the same result. So let me think. Since this is a curve, I'm going to simulate this curve here. So let's create another. End of suffering is the one we were working on yesterday. So this kind of curve is usually 1 over x. So okay, we now have to decide the what's the term? The derivation. This, yeah, it's a much flatter curve. So we'll say our x's are temperature. So we'll actually do something like this. Let's add. We say our temperature will be 0. It'll go between -90 to 63 or something. Let's be accurate. Temperature will be -93.2. This is 61.8. Okay. Now this is essentially has to incorporate T. Okay. If it's 0, of course it's infinite. What is happening here? Oh, okay, that's correct. And then it has to take into account what? Relative humidity. Here's a funny thing. In this, there is already this playing a role. You calculate this based on this and dew point, which is interesting. So we'll do that exponential thing too. Just more people to ban today from the chat because they seem to be really determined to paste really questionable URLs. So the dew is similar logic. It's 98.2, 36.8. Let's call that D. Let's make you 4. And your minimum will be 90 point, something like this. Yes, 36.8. Okay. Let's calculate relative humidity as R. And this is our good old formula. 100 times exponential. Should almost know this by heart. So blah blah blah. So we could easily take this exponent over this temperature. This is D. Okay, and then we say that whole exponent is over the other exponent. Okay, and this one is T. This is kind of correct, kind of not. That's it. Because that was like string addition. Why are you offering me this? Because you think R is the IC, like radius. Call it humidity. Okay, there you go. So let's double check some values here for accuracy. 1.608. shit. Dude. Didn't I do? Okay, I think it's too narrow. 94.14 417. This is correct. So this h has to be part of this equation. So really generalizing here. I'm not saying this is the correct format. First of all, if we say this is the general format like this, for this side, everything looks correct. This is not correct. What we need is a function that actually looks like a curve like this, which is continuous, not well, this is continuous too, but it's asymptotic here. It's kind of a bad case. I think what I'm looking for is the I don't remember what was it. This one is this one is gonna give this. This is the problem because it doesn't work with the complex numbers. Okay. We imagine this axis as probability. So when x is in the minuses, we would still like to have some kind of so then this is sounding more and more like 100 minus. We have to shift this stuff here. This can't just be t. Of course, it can't be t plus d. And okay, something was. Let's ask ourselves this question. If this was 100, right at this point, the question that I'm asking is a similar question that I would ask for rain. It's 100%. Something has to happen. The question then is, if it's high enough temperature and humidity is 100, it should rain. If the temperature is low, then it should snow. but at 100% humidity, some shit has to happen, right? For this to be at 94%, the result here is not quite correct. So it's as if this should start at H as like probability, right? Now you are kind of 94% sure something will happen. If nothing else is decreasing this, right? If this was 100%, then yeah, this is the probability function. 100% something will happen. To not be stopped, you can start with a simple model. But also I have to write the code to check against those lines too. Often writing the code is really difficult. So like I can work out every detail in the graphs. You take your graph with triple point. So I'll keep following my line of thought here. So say if this is 100, let's say for sure something must happen. Now when the dew is less, we are decreasing our chance of precipitation, whether it's rain or snow. Now, according to this, say this one, 1.6 is here. Okay, let's look here. I think I'm gonna get to the bottom of this. Like relative humidity is 94 point. Let's be. Okay. So according to this condition and this condition, this calculator gave us 30% chance. So this is what we should be getting. This result should be 30%. So what kind of monkey business should we do? We take this H 94% down to 30% is the question. It also gave us another piece of information. Melting air temperature is this. So it actually calculates this from somewhere. So this Tc is the temperature in degrees Celsius. It's like you give the temperature, some constants here. I think this is a constant. This is giving you the relative humidity. We're kind of doing things in reverse here, in our case. This calculator is based on this article. So I'll give you this link. This page has this URL here, which opens this page, which is talking about that stuff. Talks about melting points and the joules and energy, the heat, radiation diffusion, all that stuff too. So it's again, it might be overkill. The reason why I think it's an overkill is because with just these two numbers, if it's giving us an accurate enough result, so it boils down to something simple enough, which I believe is going to be something like this. Looking at the article and looking at this, there is clearly this is a quadratic function, by the way, or it's 1 over x, which we just figured it can't be. So then this is going to be a quadratic function, which means one of these values is it's the polynomial, forgot the name, second order. First order of business, I'm going to get more water. flavor-wise. Okay. Watch for the article. Yeah, okay, I'm just catching up. Yeah, the article is already here. I'm still going to browse this or sort of skim parts. The thing is, I don't have this kind of things like, well, heat flow to the flake, that kind of thing. They actually, I read this, they simplify it, which comes to something like this. Which is basically this. They simplify things. So they ask, what is the relative humidity required to keep the flake frozen at a given temperature? Could this just be the fucking formula that I'm staring at? This felt like can't be it, can it? Call this and call this one SS shit. This is exponential. Some stuff here. Some see, this part is basically multiplication after this, so it's a 10.5 Celsius, which is just hard-coded value, minus T. T is that T at a given temperature, which is this. This is Celsius something, which is 1727 T, which is this, over some other T plus, okay, so this goes to the bottom then. And this uppercase T is this. And this is nope, go up, this, not this is here. Converting an implicit equation into an explicit one with some assumptions leads to an accuracy which is quite normal. So let's make sure this equation is written correctly here. 9.5 times E to the power minus 17 over T plus some number. That's fine. We don't have to put brackets here anymore. This could also be minus here too. It doesn't matter, but same thing. Okay. Then times 10.5 minus T. So this is giving 75. Now I will use actually that's already here, right? So clearly this is not this. It can't be because this is just relative humidity. But I see. This is okay. One point six. 1.5 or 6 go up. Sort of 78%-ish. Let me take this to here. So this line is 1. This is 1.5. Then 71. This could be 202. Yeah, there's sampling there. So this is 31 or 32 difference. Keep this here. We are dividing that to 1.5.5 0.66. So we'll go along this line. So here's the intersection. Here's 70. Here's 75, 76-ish. More or less there is sampling there. Okay, this is correct. So this is according to the the equation here. Is the relative humidity required to keep the flake frozen? So the result is correct. However, the interpretation is a bit confusing. When you read a sentence like this is the relative humidity required to keep the flake frozen. Question number 1. What if the the relative humidity is higher than this? What happens? Question number 2. What happens when the relative humidity is less than that value? Which way should it go? Now, looking at this, so this 75 business here, it's marking the red line. Can we turn this into okay, let's switch this to Y. Change the color to blue. And then let's assume T is X. Now, what are we looking at? When X is 0, this is 1 here, 9.5 times this, which is close to 100%. That's why it's almost 100%. Not exactly, but there. As the temperature is rising, so X is going to 10 degrees. and the chance of rain is getting close to 0, which is consistent with this. So at 8, there's let's look here. At 8, ten, 13 or 14. We could actually do it this way: 8, 13 or 14. So I'm right. I think this might do. We could let me see, change the axis to, because we can't have temperatures more than hundreds, and here pretty much like this, right? And here too it's like probability. That's fine. This is fine. So we have a bit more, and honestly we are never going to deal with those temperatures. So x-axis, call it 30 at the most. In their view, RH is the discriminating factor for the presence. Yeah, that sounds about right. Here's that's why something kind of funny. In the calculation of this is important. Honestly, instead of asking for this, they could have asked for this and do. They could use those two values to calculate this and still come to a result. They factor this in the equation anyway, so it's kind of redundant, but it's okay. So here is here's what's going on. Let's change the tune a bit. I feel a little bit dumb because this equation that I was showing, that evaporation thing somewhere here. This is actually using the exponential function, the decay function, which gives you this form anyway. I see one issue, not with the model itself, but for a different need. Because we have rain and snow. If anyone came to the room right now and without knowing all the stuff we have been discussing in the last hours, and we made this claim, here's a graphic, a model, whatever, that is showing the chance of precipitation. This person asked the question, yes, precipitation of what? Rain or snow? We don't get an answer to that question. This is assuming that if we were only checking for snow conditions, yes, but because here's where I was perplexed yesterday, and I'm kind of equally confused too for similar reasons, although the conditions are opposite. Yeah, but see, it's a similar problem like with the rain. I understand, but we already have a similar problem for the snow too. It's all about the interpretation, not fitting numbers to a model or coming up with equations. Here's still the same problem with this graphic, like this or this. This is, by the way, a really skewed, like really zoomed in version of this in essence. Um, they just narrow this down very much. But here's the problem. This assumes you look at this line, it's like more than 100%. Okay, let's clamp it 100%. What does it mean? Below zero, it always snows. That's not the case. Or if we interpreted this as rain and we kind of reverse this would kind of go this way, which means over some degrees here, it always rains. Well, we know that's not the case. Um, like having lower temperatures is no guarantee for snow, or having a high enough RH value is still not a guarantee for rain either. So, and then introducing thresholds into this is even more scary, because like who determines the thresholds? Us or some natural factor? So we are kind of making progress, but not in the decision making direction. In more so like I'm making sense of things, but it's still a progress. Progress in the right direction. Let's see. Well, at least we have better tools. Can we something else is coming to my mind. This is a right step towards making a decision. My data, there are limits. Yeah. Well, in this situation, we are kind of doing that here too. I'm not going to look at this values, but if that's what you are concerned about, or this values. Problem is usually around sort of this range for me right now. But here's, I think, what is missing here, which might be in front of us. So let's look at air temperature, 1.6. 1.6. Right? 75%, which we confirm visually looking at this chart too. Beautiful. However, when we put this And we do know that for this air temperature relative humidity, we get 75% somewhere, but this calculator is doing something else than this result. We should be getting 30%. So this value 75% will be, by the way, I say percent, but 75 some unit. That has to be input in somewhere else. That should give us 30%. That's what we should be seeking. So when this is 1.6, and by the way, that could very well be this too. No, this is going, yeah. So that is, yes, in fact, this should be the same T, because we actually did that. This T is 75. We confirmed here, okay? The chance should be 30. So I need another equation. Is this 75? Good. I need to incorporate T and this Y, which is some RH value. We said it's sort of like a, let's call this H2. Which H are you going to use? So let's call this humidity required. Do this, where is it? Where are you when I need you? Where are you? Humidity required is this. This is the real humidity. I think there has to be some kind of relationship between this is the humidity that is required, this is the actual humidity, and in the calculation of this, these two play the role, but we are also providing this some kind of magic. We have to come up with a number like 30%. Then we can talk about thresholds, and we can say, fuck it, anything below like, I don't know, 50%. Assume it's not snowy. We gotta get to this number. This is the missing link right now. 70%, 75% is just for RH point of view. Yes, but they still incorporate that in their calculator, I believe, because honestly, if we had seen 75% here, I would say like, okay, maybe this is what they're outputting. The result of this is what they're outputting, but they don't. They still take in our relative humidity, and I think they're comparing their 75% based on like, you put in this here, okay, this is doing something. From there, you get to 75%. Then you type, like we type in 94, and it does some kind of check, and it says, well, 30%. Where is this 30% coming from? Because this 30%, according to this graphic, doesn't, like, there's no correlation between this and the probability. There has to be another axis here. So let's call it probability P equals it sounds dumb, but say never. Just arbitrary fudging numbers now. Let's fudge some more numbers. We do know this is working just fine. Let's go for it. This one. Okay. So it snowed 2 centimeters somewhere here. Highly likely it snowed in one of these 85%. So it's -5, -7, right? Plug that in. Um, good. It's 5, 7. So relative humidity is 85. 85. Perfect. So type in 85, 85 here. I don't think they accept decimals. -5. What does it give? It will snow. Guaranteed. And actually make it 85. It will snow. What do you get? 18%. So this equation is clearly not correct. This was too stupid of an equation anyway. Shame on me. By the way, I want to point out something. When we give -5, look what happens to their equation. This is no longer positive. Because when this was positive, this difference would be bigger than 0. Now this is 15. Okay, 15 and a half. With -5, this is still relatively high. But this is now positive. Okay. Now exponential minus would actually be decay, but now this is positive, so this is a crazy high number. And here's the result. It's a crazy high number. It's 213. I'm not that ambitious. That's shit. But here's something like I'm just pointing out something fundamentally wrong. I think these guys are. I just noticed something which proves my point. Look at the title. Look at the URL. It's snow above freezing. So as soon as you put temperatures below 0, this equation blows up anyway. Because like I said, I'm pointing out like this, there is no such relative humidity 200. It could be max 100. So this can never be minus. So this is they're always assuming in the minuses it will snow, which is bullshit. We know that. So this below this layer is garbage. In the minuses, this is garbage. Garbage. Okay. So that was something. This graph. I don't think so. Mesoscalic. maybe. This is a different paper. It's about snow melt. Um, Mind you, they kind of talked about melting point and they reversed the logic. Let's simplify this stuff here so we don't need this garbage here. Um, Maybe we don't need the page numbers yet. The third paragraph below the graph. Yeah, if the temperature does rise above freezing, there are no parameters with which the type of precipitation can be determined for certainty. Which is my earlier point that is it rain, that kind of thing. The use of frozen bulb and this wet bulb and dry bulb thing keeps coming up. This is the same calculator as this one. This is what I'm using in evaporation here. All this about that. It's incorporating humidity, temperature, wind speed, uh, surface, pressure. So at least 5 things go in this. I think when I say relative humidity, I mean also 6. It's the dew. Um, yeah, air pressure, wind speed. There's surface, just coming in here. Okay, let's do a basic test here. I'm imagining a few potential solutions here. Let's go to the beginning of the file. Let's say it's 1 0. It's 1 and 0. Because we do know that d can never be over t. D equals t is 100% case. It's fully saturated, that kind of thing. Now, I was when this t was x, it was simulating the other case. Okay. Now I'm going to do something dumb here. Call this y. In fact, when this was 1.6, I'm familiar with this number, so I'll stick it there. Not this one, 1.6 to 0.8. So let's go back to those original values. This is real humidity. This is the required humidity for keeping the snowflake frozen. In the comments section here, there was an explanation. Thus, if we wish to observe warm weather snow, very dry conditions are required. They kind of mean very dry here, not here. Because, for example, if the ground humidity is only about 20%, so that's kind of contradictory, as they are saying, well, you cannot really have that. Well, by looking at the graph, you must have, but it doesn't happen because as a first model, you would take the triple point one, 2.1. Which triple point one? The three phases. I looked at that hours ago before you joined the stream. In the first hour or so of the stream, that turned into a bigger mess because that was like done in the lab under no real atmospheric conditions. The temperatures here are not really correlating to the three phases. It's a different environment anyway. So in fact, I still have those screens open. I think this one. Yeah, we were looking into this. That's when with another viewer we investigated whether we could simulate this transitional phase here by thinking that snow starts to come down at a higher altitude, therefore the pressure is low, whether it has any impact on it or not. Well, according to this, it has. Because then we by checking values, we got to different weird results, like normally around 0, right? Like here is kind of weird. Like we cannot assume this graph can be applied to the atmospheric conditions for a good reason. I'll tell you why. 0 degrees, this is the normal pressure, right? This is an average day ideal conditions. This is the threshold where a little bit here you have liquid water, a little bit here you have solid water, ice. However, this cannot be the case in the sky, because then the whole sky is either frozen or the whole sky is just fully rain. We know that the sky conditions is mostly vapor. So then whatever is happening up there is happening in this zone. And then it turns into a whole other mess where, okay, we know for real that this is the case. Now, we don't have those numbers. How are we going to approximate favorable conditions that meet the observation from the values we have? That's a whole other exercise. So this is under sort of lab conditions. Like these conditions, for sure, it exists up in the sky. It's just that the data we have, we are never going to get to simulate this. So let's see. This one again. Okay, I was reading something here. 20%. If the ground humidity is only about 20%. If we were to seek precipitation when this is 20%, there's contradiction, because if we expect precipitation, this cannot be 20% because the atmosphere will be wet, which will push it up here. In that case, yeah. So if there's precipitation, naturally it will be rain. That's really what it is. So. Yeah, that's why I sometimes hear, yeah, the weather thing is really weird. I had a friend. This was like 20 years ago. She showed me some of the equations, and she always talked about like these are always approximations. They never really knew it for sure. Um, and it's still one of those things that supercomputers and whatnot, they try really hard to model. Whether we collect data, but coming up with forecasting models and all that stuff is very difficult. That's what I know. And now you have really advanced equations, like say this calculation that I'm showing you. There are like 7-degree functions here. Well, because it says 7, but I put it there so that I know it's the 7th order. So yeah, some crazy stuff. Let's see. We could, of course, oversimplify things for us. This is so I think I'm going to write 2 equations, and so far, this is a good step towards understanding uh, the probability of snow above 0. That's a given. Okay, that's done. Ish is done here. The result we get out of their equation is 75. Um, The difficulty I have is based on this explanation. If we wish to observe warm weather snow, very dry conditions are required. So it's as if it should have been 75, but we are at 94. This is too wet, so it can't be snow. So this has to be close enough to this, then it would snow. So this is maybe what I can do to say, well, over 0, how far off are you from the happy case? Now when I increase this, let me undo that first. Let me take the difference between H and HR, funnily enough. Take this, put here. No minuses, no monkey business, just this. Okay, smarten up. Yes. Okay. Is this difference going up or down? When the temperature is going up? Okay. Naturally, because when the temperature is rising, there's even less. I expect this difference to go down. Again, be careful. This now. Okay, now. Let's say this is 0.5. This should be 0.2. Okay, does my game need accuracy? It does. It doesn't need. It requires consistency more than accuracy, but it requires accuracy, and I'll tell you why. I'm providing. I'm gonna give a chance to the players to, if possible, play the game in their own city. So if you are from Toronto, the game should have Toronto, city data, weather data, all that stuff. So when you want to grow tomatoes in Toronto, you have a very short summer season. That's due to the fact that, yeah, you get the point. So I want to have the real weather conditions simulated in the game so that I don't arbitrarily say, well, you have only 3 months in Toronto to grow tomatoes. That has to be determined somehow, not arbitrarily by me. So I could have the flexibility to incorporate different cities without understanding each city's conditions, because I don't want to study city after city to make some hard-coded choices. And of course, once the system is done, I will just apply this to the rest of the cities, so all these things will pay off. Like that's why I'm taking my time here, because then it's like the floodgate. I will just apply this across the board. And this is something that I'm seeing right now here, happy case with this equation. As we are seeing in the graphic, as I'm approaching the 0 and my margin is getting smaller between T and D, which is pushing the real humidity to 97, but also it's pushing their calculation to like, whereas this was 94 when was 1.6 to 0.8, although there is practically a degree difference in both. This is relatively the same, but their 75 required humidity has gone up to 91, which means the threshold or the margin between these two which is this, is reduced. So maybe this is going to be my threshold, and I'll say when this is less than 10% and the temperature is over zero, snow. So that's kind of a happy case that I hope I can fine tune those values based on this sort of like observation. Then the remaining question, of course, is there has to be something similar to this done for minus t. And I think we could get that done too. Question is, dinner will be a thing soon. I don't know when, but soon, maybe in 10-15 minutes. I think I will continue after dinner, but that means 1 minute? Okay, 3 minutes. So I'm going to put the stream on pause, and we will meet after the break. Okay, I think I have a plan. So let's create some if conditions here in the graph. I also understand what you're saying, Fabrice. Um, I have a new idea. Well, more or less. But I agree with your with one of your latest statements that I will have two models and I'll mix them. One is for conditions when the temperature is over zero, which we seem to be doing fine. I have to narrow this threshold value to a certain value when it makes sense. In the other side of the equation, when t is less than zero, I will come up with a different model. Either way, you're right. I have to check it against my data and then adjust the two models. So luckily, in Desmos, you could do if conditions. So let's say something like, well, y is, let's say 1 if t is more than 0. Was it like this? Something like this. Or I have to look this up, but there is a way to write if conditions, if statements. I forget the syntax. Comma, yeah, and then there's colon. So if it's less than 0, it's x cubed. It's this formula. If it's so it's 2x if x is between 0 and 3. Yeah, so we'll do something like that here. So if it's more than 0, then we say it's 1, or if t is less than or equals 0, then we say fuck it, it's -1. Okay. So this way we can do something like if t is here, that black line is always 1, and if it's less than, then it's actually -1. The scale is a little bit off, but we can exaggerate it here and say -10 or +10. Okay. So I will write two models, and both models will be put together like this. Either way, I'm expecting to see some kind of 0 to 100 range here. That will most likely show me the percentage chance of snow, that kind of thing. And then the snow amount calculation is a different business. When t is, maybe this is where I'll do equality. When we say 10 here, this could be another function. I will call this y of positive temperature. So it's y of, there's a shortcut to trigger this, but y of positive. So we could easily say instead of 10 that so now to look at the black line, we would like that black line to be as close to 0 as possible. Or we will do an inverse case. We will want it to be as close to 100% as possible, indicating that it is supposed to snow. So this happens when, in my interpretation, T is close to 0. Like this. In fact, let's reverse the case. So say instead of this, we should perhaps do this. Okay, but no, do the other way around. Okay. Let's save this. Good. This is a garbage quality. This is real humidity, by the way, and this is now let's interpret this system based on this graph. I'm going to type in something like 3 degrees. So we'll be somewhere here. And that somewhere will be then we will be around 50, 55, 57, 58. This will be 57 and 58 when temperature is 3 degrees. 57, 58. Perfect. What is missing in this story is when this is the relative humidity needed to keep a snowflake frozen. However, we don't know the real humidity that is calculated with the dew temperature. Now, when the temperature is 3 degrees, air temperature, it should be like something like 30 here, right? It's not. This is a minus. I mean, dew could be anywhere equal, close, or less than T temperature. So we could pick an arbitrary value, to be honest, as long as it's not more than temperature. So this is actually fine too. As far as reality could go. In fact, if I recall, there is actually a day here, a certain hour, where temperatures were in the positive and dew was minus. The reason why I'm talking so much about this is because the way we should interpret this value, essentially. Okay. Now, trying to make sense of my model, it kind of checks out in my mind. I'm having a hard time articulating it so that it makes sense to you. When it's 3 degrees, let's actually look at it here. For the snow to happen, um, we need to have higher humidity. We are just at the threshold here, right? Here you see this in this between, like in between zone. Um, we have snow, this snowfall, this square like shapes, right? Anything higher than that, then you go into the rain. Too much humidity and you'll have rain. Just enough humidity at this degree, you'll have snow. Yeah. Interpretation wise, when this difference is big, there isn't enough moisture in the air. When D is approaching T, real humidity will approach saturation point. I think, yeah. So let's see what happens to this. This is gonna approach 100. This should stay the same because that depends on T. So when H is increasing, H minus HR will be getting bigger, and this is gonna get smaller, this. And that's kind of what I'm expecting or hoping to see, because at that temperature, you go high, you should have rain, therefore less chance of snow. So if I'm attributing this to the chance of snow, this is supposed to go down with D going up. In fact, when D is the same as T, 100% saturation, it's just too far off, and this is already 57. So when the dew is going down, by the way, this should never exceed 100, but so here's an interesting case. So according to this logic, it should snow. Kind of what I'm understanding. And here, definitely it's snowing. So let me differentiate some of these cases. So I want to duplicate this. Can we do that easily here? Do you have something like that? Let's introduce P positive. Okay. Equals 1.8. Minimum could be 0, maximum will be 10. Steps could be, or should be 1.1. Okay. By the same token, let's do dew point. I think in this particular case, dew point could be in -5. Maximum will be the max of TP, which is 10, and this is 0.1. So this TP and dB has to be here. Okay, done. This is the number I remember. So we could fine tune these things. This should never be more than TP. And this is the case when it's over 0. So I'm going to do some tidying up here. I need folders. I will put the constants in its own structure here. I'm going to what's happening? used to so how did I group the other okay, now you're in one. I see. So you do this and we say constants. This is a constant. This is a constant. Here are two more constants. Okay. Then there's an over zero function. Please go away. This is relevant, right? I will change this to Z so that it is the humidity required when it's over zero. That same Z is going to be incorporated into this. Not right there. Here. This P is the positive case. Again, I'll consider this as Z. This is the Z case. Okay. This is not correct now because I have to change this D to. Here's a funny one. This is always going to calculate it regardless of T or D being over zero or below zero, but I will make an exception here. I'll say this T is for the negative, or it could be negative. We are still not answering the question whether it should snow or rain. Let's keep this as a continuous. What I'm going to do here is this H is true for this. There should be another H for positive. When T and D are positive, this is the continuous T and D. But this H that we are using here is asking for the positive value when the T and D are positive. So we need another expression. So we'll call this when humidity is positive, meaning it's actually everything here done with dP. and TP. This should be equals. Okay. So this checks out. So now this should be h of p. Right? And y is a linear value. And there's something wrong. You've defined HP in more than one place. Have I? Oh, this is what the. So when the temperature is positive, HP is this. When it's continuous, including negative values, it's this. In fact, this two should give the same number when this is 1.6. This is 0.8. Correct. Oh. Yeah, I'm not differentiating between these two, right? T is right now positive because I said 1.6. So it's taking YP, and YP is what is YP? Positive, which I turned it into Z anyway. Okay, which is this. So it's 80 something. This is when T is positive. Is T positive? It is positive. That's good. So this kind of works as to sort of in conjunction, right? If I pull this around, as soon as this T is over 0, my final equation here is outputting the value of YZ, and YZ is using positive values. So as soon as this is over 0, the correct equations are using these values. So, and this can never be less than 0. And when it's less than 0, this here is going to have its own equation, which is going to use these, but not these. So this will be insignificant or irrelevant. The only thing that I'm probably messing up here is the E and Z. So this is the over 0 equation. This sort of was necessary because of this. Okay, this is okay. This is not going to matter in Node.js or Godot code because I'm always going to refer to the exact TND. This is for us to make sense of the model. Gotcha. Now, here's the thing. When D is approaching 1.6, we have more saturation. With more saturation, this is going down. With more saturation, the chance of it getting small. With less saturation, we are looking at YZ. It's warming up, we are decreasing the chance. It almost feels like 95 will be a good threshold for us. You do not understand YZ. Well, I'm just, instead of having smaller values indicating the likelihood, I reversed it so that higher number would feel like there's a higher chance. It's readability purposes for us to make sense. And actually kind of corresponds with this data too. Because I was looking at the difference between the required humidity and the real humidity. When that difference is getting narrower, there's a higher chance of snow. So I'm inverting that difference. So instead of like saying, well, having 6% difference looked like a better case than 18% of difference. So I'm subtracting it from 100. So it actually reads like there's a 94% chance of snow versus 82% chance of snow. So it's human readable. So let's simulate this case. 4 degrees. Again, here, according to this, we shouldn't really have snow. Simulate it. P positive is 4. We don't really know this. We are arbitrarily choosing it like 1 maybe. Then we'll see the relevance of this soon. This is the humidity that is required for snow. But this is the number we have in reality. This is how much humidity there is. So according to this logic, there's 65% chance of snow, which is slowly becoming like the threshold value. Well, not 65, but so to increase the chance of snow, which is here, the dew has to be smaller. So then you're increasing the chances. But for this to be, I don't think this kind of exists. I don't think there's this much discrepancy ever. It's like I see 4 or 5 degrees difference. So this is like pushing it. Okay. And then this is still not high enough, which is consistent with this. So that at this temperature, it is actually rare for snow to happen. So there's something nice about the model. Now let's take it to 1 degree. Okay. At 1 degree, you most of the time there's like all these snow marks here, right? Markers. Semi probabilities, not quite. Take this down to 1. So there's something okay with this, like right now. Let's say dew is -2. As the temperature drops, the likelihood of snow is increasing, which is actually consistent because that's what dew is, right? It's gonna start to dew. So in fact, if we get to 1, we are at 100%. So we'll assume anything over 95. We don't care if this is over 100. We only care for, this is not about accuracy at this point, but this model seems to be okay right now. Interpretation wise, it fits the observation. So when you get to 1, it is going to snow. And even if dew is rising, and let's find that sweet spot, 95% ish here. This still seems okay based on this that I have seen. We have sort of positive to negative things in some of the rows. HP and HZ are probabilities. They are well, they are not. Well, they are actually relative humidity. If you consider relative humidity as the probability, I think that's what you said. They are using relative humidity here as probability of snow. In that sense, kinda, but they are technically not probabilities. They are still humidity values. I built a model here where the humidity still plays a role in determining whether it's supposed to snow or not. Here is where they don't actually tell you. There's a missing link here. When they look at this sentence, there's something missing in this statement. The missing part is this. When it is required, this is the question I asked actually an hour ago. What happens the real humidity is below or above this value? And based on the later paragraphs, it looked like this is the required, and if any real humidity is higher than this value, then you don't have snow. So you want things to be below this. So that's the model that I have. So I'm looking at their difference. The difference between these two is roughly 5%, and I'm reversing that 5 so that I could get to 95% probability of snow. If the difference here is increasing, then this is also decreasing, because this is always reverse. Does it make sense? Yeah, so in a sense, how far off these two values are. Or these two values, HP and HZ. I talked about the right thing. I pointed at the wrong few things, but the logic checks out. And also looking here at 0%, the probability should increase immensely. Where are we? Here. That's what we have. This going lower is making things even in more favor, and this is 0, and then it's like, okay, we surely have snow. This checks out in my mind. It checks out, man. Like it doesn't. it doesn't look intuitive, but it really checks out. I mean, the whole thing is kind of messed up anyway. But so this is when temperatures are over zero. So we use one of the equations here, which is doing this sort of distance calculation. How far off are we from this ideal RH for snow to happen over 0 degrees? Now the second half of the model will be when temperatures are below 0. So now I have to come up with a new group here, and I'll be using that instead. So this is going to be this is kind of going to be the real y. YZ was when temperature is over 0. That's kind of what I did. I could have typed P there for positive. Maybe I'll do that later, like YN and YP for negative and positive. The problem started to do when I want to differentiate HP. You know what? Maybe I should do that. This is always the H positive. P positive, positive. So mark this as positive. So then this, see, this is it. This is where the discrepancy was, yeah. This HZ is their required. How about I call this F? Freezing humidity. So then this should be F. Good. So this Z will be positive. This will be positive. Done. Everything else is positive. And now we can now talk about the negative. So imagine we have another function here. And it's negative. And I'm just going to put 29. Instead of using this, we are going to put y when the t is less than 0. And this is controlled by this guy. So if t is positive, we are using the model offered by this guy. If t is negative, we should have this. Now we are going to run a different probability function to check the probability when the temperature is less than 0. So this is our if-else case here. And when it's over 0, this is controlled in its own fine-tuned temperature controller. This range is just too large for me to fine-tune the values there, decimal values. This is really, now it's gonna get crazy because let's see, it's of course I'm hard coding minus 29. This should be brought back to this area. This is my chance to get water and think of the function. Okay, so do you get much snow where you live, Fabrice? Sorry. Get this. Let's ask one of those simple. Do you get much snow where you live? Maybe I'll put your city in the game too if you let me know where you live. Ah, just generally speaking, country might be enough. You want you don't want to disclose personal information. Um, let's type a dumb Google question. When does it not snow? uh, when? Why does it not snow when it's too cold? Because there isn't enough moisture, and maybe we'll understand the dynamics. It is just not true that it can be too cold to snow. Colder the temperature, it reduces the ability for the air to hold water vapor. Just it's about thresholds. This is what we are after. Yeah, because it's too dry. Hence, I think I misinterpreted something here, which I might have to fix in Godot, but maybe there won't be a need because we only call for the type when it's supposed to snow. If we say if it's not snowing at all, it doesn't matter what I'm returning here. Right now, I'm assuming this is applicable here too. But if the system is off, it's not going to matter. So in other words, here, um, when it's this cold, and let's actually keep reading because it's about um, the science of it. This sounds like a good question. Yeah, this is something I observed in Toronto too. When it's around minus 20, 25, that's like between 20 and 10, then we have the snow. But if it's below 20, then it's just cold. It is usually clear and sunny. As it's warming up from here to here, there's a chance for air to hold moisture, so then it comes down. So let's tie this to this yn. Let's attach this to h. We do it as h. Yeah, h is the continuous humidity second. How is h over some negative number? This is approaching 0. Sorry. This is still positive. This is the almost 1, which is 17 over low number, but this is still okay. This is a negative number, which makes this more than 1, hence over 100. Oh, that's my bad, because what did I have here? And this can't be negative and then this positive. Yeah, this is wrong because this should have been like. Is there tabulated data for this picture? What picture? This Desmos picture? This Desmos? Because tabulated, this is sort of tabulated, if that's what you're referring to. Pictures, this. I'm looking at the timeline when you wrote it and what I was doing when you asked that question. I think I was still here. Okay, so this, when the temperature is positive, the way we are mapping this to the humidity is kind of okay. I mean, it's not correct, but oh, I confused myself again. I'm thinking, why is this not moving? Because we are in the positive temperature, so the other one kicks in, which says there is 94% probability. That's it. So I have to keep this. I need to rename this. This is snow precipitation calculator. Snow precipitation probability. It calculates, does something. So this has to be lower. Okay. Because I'm still hoping for the rain to be merged into this model. That's a later phase. So based on my experience, say minus 26 dew, minus 20. Here's humidity. Actually, let's look at the weather outside. I mean, it's not snowing, I know. The picture with different kind of snow. This one? No, there was no tabulated data. There is only this degrees here, and this is humidity. I actually eyeballed it. They put 3 or 2 dashes here. I thought they actually meant 1/3 and 2/3, which is like 100% humidity, all this line. So then I basically wrote if else cases here to say between 0 and 3 degrees below 17% humidity, it's sort of this shape. This is all done, like last week this was done. But it doesn't actually really show you the exact values. This is the problem that I'm facing. Nobody seriously has correct model, correct equation, correct data. It's all spread out. It feels unreliable, underdocumented. And if anyone wants to get serious about like understanding weather to do something about it, either someone or some institution is hoarding that data, or we are really hopeless, because if this is the best we can do, it's fucked up. This chart, by the way, was done by a Japanese scientist in 1954. He wrote a book. You could still find the book. It's on Amazon. Forgot the dude's name. He wrote a whole paper about snow types. This guy. This is the guy. So his book is on Amazon, if I believe. This one. So if he could pay this much, he could own it. Uchikuro Nakaya is the guy. So there's even a picture of him, I think, in his lab. Somewhere, like looking at the crystals, and for me, this one. Whether it's him or not, I don't know. This picture was coming up. That's the science of it. Okay, let's look here. This is actual data. Right now in Toronto, 10 to 7 in the evening. Actual air temperature, dew point. To type these values in here. Minus 9.5. This could easily go in decimals. And then the dew is 15.7. Right? Right. So this is the humidity, which is 61%. And it is correct. And yet we know there's a low chance of precipitation. It's not snowing. In fact, I'm actually going to peek out. There is no snow. There's no rain. Low chance of precipitation. Now we have to consider this in terms of percentage, and then it goes into even more kind of like less likelihood zone, right? So this is apparently not enough for snow to happen. Just too cold, let's say. Let's check next hours. Yeah, it'll be cold in the morning for sure. Because they cannot due to chaos theory. Who cannot? Oh, the authorities cannot come together and figure it out. That's I was ranting about that. I guess you are referring to that. Chaos theory. So everything has to go to shits, right? That's what you're referring to? Chaos theory? So it's cold. U is here. This is the humidity. There is no snow. When this is gonna approach small value. They have different names for each state of snow, if you remember. Um, it says if either one of your messages is missing or my stream is coming to you delayed. Because what you're typing feels to me like it's about something I talked about 2 minutes ago. Kind of curious about that. Like your last comment about each state of snow, it feels like it's been ages since I showed you this. Because I think I felt a bit confused when I talked about the weather data scattered and disorganized, that kind of thing. And then you talked about chaos theory. That felt like delayed too. Not sure if it's something I have to fix on my end. The stream is delayed. So this person was saying, as I experienced in Toronto, when it's really cold, it doesn't snow. Let's do that case too. We are still outputting H here. Let's do 60. This is actually different because I changed the numbers. When it's this cold, of course, when this is going to approach, you know, could we also assume the 95% here too? I'm going to look at a different year in Toronto. 2008 was a particularly snowy year. 2008. What is amusing is the nil value. Yeah, I think it's clear you're you either rewinded the live like the scrub on YouTube, that you're not at the end of the live stream, because I talked about the nil value like a minute ago or two. This one. Yeah, they cannot predict for sure. It's about probabilities like this. But I think my stream is also either delayed or you scrub the timeline maybe a minute before the end. So 2008 Toronto. Let's look at this Excel file. And we had a lot of snow. And here is my beef right there. When I was talking about the other day, yesterday, sometimes they mark snow as like the previous 24 hours value. Sometimes it's like this. Right? So it's inconsistent. And then you have gaps like this. 24 hours, 9 centimeters of snow. Things like this. But let's focus on this area. Here is, you know what? Let's do the cleanup here so that we get rid of these 9s. Run, 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 run. L1 here. Okay, it's either here or the other one. This one. It can't be this because there is 0. Let's focus on this. Okay. So let's look at the temperatures. 1 degree, 0 degrees, 0, 0, 0, -1. And yet somewhere here, we got 9 centimeters of snow. -1, -2, -1, -3. So based on the pressure change, I would assume that it snowed more here in the 2/3 than in the last third. And it was also getting colder. And the difference between temperature and dew is increasing. So when this difference is increasing, there is less chance of snow. This is also another indicator to pressure. Okay, now this is good because it's right at the threshold, right? Sort of almost positive temperatures, and we are going below zero, and we have snow here. Then I will check the next days, like actually next day. Perfect. We are approaching -10 and 14, right? And yet we don't have snow. It's just too cold. But that is due to the fact that dew is also the discrepancy is getting higher. The pressure is getting higher. So this is actually cool. Okay. I can do something with this. So when this is increasing, relative humidity is sort of working like percentage. Let's do this, let's say -1 to that's okay. -1, -2. Where are you? -1, -2. What's the 90? Or we can fudge those things a little bit. We'll put some kind of modifier there. Why? Okay, yeah, there. So let's try this. -2, -4. I would assume the chance of snow is decreasing as we go down. -2, -4. It's decreasing. That is good news. Why is it fluctuating? Okay. -2, -5, we should have even less. That's regard. Like, I mean, I'm not even going to simulate that. But we cannot set the threshold to 95, just like we did in the positive, because we still expect to see some snow here. These conditions are still okay. So I'm going to create some arbitrary threshold here. Let's say it's like a good value. So when it's 2 to 6, we don't have snow. So this is 75%. So when it's over 75, it snows. This is sort of a general statement. Now I did see snow at -10, and the dew was like this, and it could even go this. I've seen -10 to -15 borderline snowing. Okay, that kind of checks out too. According to this, humidity, but we still cannot. If we assume 75%, right? This is not enough, therefore it shouldn't snow. We don't really need to calculate another probability. Um, is it like this? Yeah. Oh, sorry. That's it. And when you go in the positives, there is this is going to be arbitrary, but I think we can do this. When the temperature is over 0, we have to check for that other calculation, and we'll say if that number is more than 95, it's snowy. Temperature is less than 0, then it depends on the relative humidity. If there is enough saturation, regardless of where these are, let's say these two are close enough that it's over 75, this is when we'll say it snows. But temperature being less than 0, but there's too much difference, there isn't that much chance for snow, which is consistent with the existing conditions, observed reality, and historical data here. So when the discrepancy is 4 or 5 degrees, then you quickly go below 75%. So that like I'll test like -10 to -15. You are kind of right there, 75. So one notch here, it may snow. Here it doesn't. So when you take, so this is still, let's say this is 4, but when this is approaching, when D is approaching T, when this is 15, but this one is approaching D, I'm not actually checking the exact values. Let me check those. This is 72. 0.3, still the same difference. Yeah, this is a slightly better condition. This is higher than, well, that's because the formula is not the same. Well, the values are just giving you a different result. Close enough, but to exaggerate the meaning or the effect of D approaching T, we could multiply D by 2. So then every D contributes twice to the probability. we could do that. So that would be for H negative. Still similar formula. This. Right? Expression. So you do it like twice this. It's this. That's it. Go away. So look at the difference. This used to be 72.5. Oh, by the way, no, I did the wrong thing. This is gonna be okay. And this is also multiplication. The same thing anyway, but it's smart enough to understand the meaning of that, but sanitize it a bit. Although I have the right intention, I may have put the multiplier in the wrong section. Which is weird because why am I multiplying t by 2 but not t by 2? So let me write this down. There's something interesting going on here. I need to visualize it. So when t is minus 11, t is minus 15, the absolute difference is still 4. But I'll call it ABS absolute. H is 72.33. And I'm calculating this H used to be, this is the continuous, but it's so essentially negative. So I'm making an exception here to accommodate for the doubleness. HN now is 48.3. So when this is minus 10, this is minus 14. Difference is still 4. H is 72.5. HN is 48.9. So it's still small difference. Let's change this to minus 15 or 16. The difference is going to be minus 20. See what's happening there. H is 71. 29. This is getting smaller. A lot smaller than the other one. You gotta go. Remember Occam's razor. I will try. Thank you for your help. And assuming you are going to bed, have a good night. Good sleep. May you have a rainbow day tomorrow. So let's do the fluctuation here to 17 to 21. Absolute is still 4. H is 7107. So there is very marginal change. But the 44, that is also marginal change. So once you are hovering around similar values, it's fine. But changing, coming from -11 to -16, that made a significant change in HN. Now I'm going to do -22 to -26. Still the same 4 difference. 69.96. 40. So we drop by 4%. And then we do 23, 27. So in all these combinations, I'm going to decrease the absolute difference to 2 and see what happens by approaching D to T. Is this significant jump, 83. I'm actually curious about this one. 63. Next thing is -22, 24. This is still 83, so that's pretty much the same. This is 64. I am assuming it's snowing at this degree. I'm seeing a pattern here. It's as if this is kind of determining now. Maybe this is like the 50-50 chance, right? When this is over 50, it snows. When it's less than 50, it doesn't. I'm going to go back to the -11, and then I'll do the -13 case here. At this temperature, I would expect it to snow. Consistent here. This is also okay too, because it's 85 kind of thing. Because when this is -15, it's cold enough that this is going to be below. Okay. We can either go with the 75 threshold here, or we use this as like over 50. Like right around this, it should snow. So we can go two ways about this. So this kind of more or less guarantees when we are going to have snow. So okay. No snow, no snow. Well, definitely no snow. Like, look at the difference. Getting there. Somewhere here, when we have 2 degrees difference, this is gonna jump over 75, and this is gonna jump over 50, and I'm assuming that's a good. Oops. Yeah. So I think we have a winner. If this is too arbitrary, let's set this to exact degree. Yeah. This is a bit more precise case. I think this is sort of like too narrow a margin to decide. I'd rather have this to be a bit closer, so maybe we'll have the decimals here, just like we had here. Let's go with the point 5. Say minus 29 minus 25. Okay, with minus. Didn't I say half? Dude. I'm really not sure why it's ignoring that. It's as if it considers this as minimum and then goes up. So kind of screw you. Okay, argument's sake, this is 0. Don't need to fight with that. I know they are set in the app, right? So this is okay. This is what I'm after. So this is colder, no good, no good. 3 degrees. This is perhaps too close of a margin. Maybe 2.5 degrees is a much better case. When it's this cold, you want it to be a bit closer. Yeah, this is still not doing half, bizarrely enough. So when I say 7.5, still good enough. So 2.5 degrees is much better than just the ballpark 3 degrees. Here. See, this is a bit. This is a sensitive way of doing it. Of course, by changing this factor, you can make this better too. So perhaps this could also be threshold too. So say, if it's less than minus 10 until minus 20, use 2 or use 3. In fact, we could actually test that here too, while we use tools like this. So we can prototype. So I will call this H call it U. Same milieu, but let's see. This is changing. Okay. Yeah. Now, with this, this value has to be even closer for this to be over 50. Which is kind of interesting because as it gets colder, you would want this to be. Yeah, that's what I'm going to do. I'm just going to stretch my legs and come back. I think we have a Wiener formula there. So let's turn this into so for every 10 degrees below 0, we want to increase this multiplier. There's going to be some constant here. In essence, the reason why I'm doing this is because as it gets colder, you would want this difference between T and D to be closer. You want things to be saturated so that it snows, because it's a harder phenomena. To make it harder, this coefficient applied to the h function is doing that. So we could say, and because that's an arbitrary thing, we could easily change that value too. So instead of saying every 10 degrees, we could say every 8 degrees. So then things will be even more drastic. I want to keep this first, and I will create a difficulty coefficient, or it's what would you call it? Saturation. It's S. It's sort of the S factor. So between 0 and minus 10, it should be 1. So we are essentially dividing T over minus 10. And we want to take only the remember, this is happening only in the T minus, like T negative values. So this is always going to be positive. So here we would like it to be harder. So this is going to be rounded up. I don't know if there's a roundup function in Desmos. There might be a seal functions. Sticks. This is seal. There you go. You just do what? Seal. Okay. Yeah. So this is going to be sealed. Okay, done. This is the S, which is going to be used in this too will be S. Okay. Go down. Now it is really hard right now for like in this temperature to snow. D has to be very close to T. If it's actually if it's going away, you lose the probability of snow. We would expect this to be over 50 or this to be over 75. By the way, this is not the same formula as this one, but we will either use this 75 ratio or this 50 ratio. So when you get to a bit warmer temperatures, right? Even here, you will want the D to be close to T, and here it's not good enough, and here I think it's going to be good enough. Yeah. Here it's really favorable, and here guaranteed it should snow. It's 100% for both. So then you go down to minus 14.5. Here there's too much difference. This is less than 50, and in fact this is less than 75. One here, almost there. But we are most likely going to use this. And here it should definitely snow. Yeah. We are actually doing this so we could fine tune. This was a little bit arbitrary. Let's go 11. Okay. Again, too much difference. Just around the corner, 14, it should snow. Then when you go to 10, actually curious about this case. It should be okay, 1. Which is essentially this case. So these two will be the same. Here, we're still going to look at this one. But here's the problem. For this one, we assume over 50 it should snow. It's such a big difference, it should not snow. This something didn't quite check out here. Let's close this one. It should snow here. Okay, everything was going fine until however, this in my mind, experience wise, it says that when S is 1, this should be more than 75. When S is higher than 1, which only happens in T minus 10 and less. Okay, because this didn't really check out in my mind. This, it should snow now, not now. Okay, so this is a lot of else cases. We'll get it done. We'll get it done. check something. Cool. So how much of this can we do in Node? We say it snows or not. So this is still for determining these values. So let's write a new function, which is saturation factor. Okay, let's start with that. Saturation factor is this CLT over minus 10. So it's get temperature for the record. We are going to pass the record. The same record will be used to get the temperature. This is over minus 10. Okay. And we are sealing this. This is when things are in the minuses, but there's a separate check for that in a different function, which is most likely just below determine snow. Okay, this is going to return this S factor, which is then used in RH. Now RH this is essentially again the same formula. There's only S here that is different. So I can let's keep these excuse me. So what happens T is over 0. This is going to be something minus, so it's going to look awkward. So we can do a fail safe here. Where else are we getting RH? allergies. Yeah, let's be safe. If the temperature is return 1, if um, sorry, I'm still writing it the Godot way. Return if temperature is absolutely less than 0, then return this, else, which is temp, else return 1. Okay. So this will make sure that until -10, we are still in the 1 saturation case. So this is solid. Okay. Determine snow. If you should also store temperature here too. If temperature is like this, okay. Let's write the else case too. If that's the case, then we are gonna do a bunch of things. And probably after that I will conclude the stream. This may still take a good 15 minutes or so. There's this HF function, right? Which is required humidity. Var required humidity. I know maybe I should write let and whatever, hoisting, JavaScript, whatever. I don't care. Write shitty programming languages. Sorry, less shitty. Required humidity, okay, which is this formula. 9.5, oops, times math power math e to the power what? Minus some stuff. Which is the positive temperature times this. Okay. This times temperature, which is temp. And we know it's positive. This over some number plus t, which is temp. You gotta make sure this is together, otherwise you would first divide the number and it plus temperature. We don't want that. This is all together multiplied with temperature minus here. Okay? This is required humidity. Now, what we are checking here is whether this ratio is over 95 or not. So we do some kind of check here. We say var precipitation probability. Say 100 minus this HP is this madness, which happened to be the same thing as before, but it's for the positive temperatures. It doesn't matter. It's our same thing here. Saturation factor being over temperature being over 0, saturation factor will be 1, which will make this a normal humidity. So we'll do something like this. Var H. Okay. So this is your normal RH. Yes. This HF is exactly what we calculated, which is this required humidity. This is relative humidity, this is required humidity, and their difference is the probability. So we do something like this, pretty much like this, which is kind of awkward. If precipitation probability is over or equal 0.95, make sure this is 95 because I did this right. Done. It's 1, otherwise it's 0. Later on, when this is 1, we are going to do some calculation for the snow quantity. Right now we only care whether it does snow or it doesn't. So this is done. If it's less than 0, we still have saturation factor. Yeah, we could kind of do a little bit better here. Saturation. I'm passing the record here, right? For the temperature. Okay, one step at a time. What if I calculate saturation here? I say var record is and this is not going to be necessary anymore. Saturation factor maybe doesn't take the record, it just takes the temperature. Which is here. So then get temperature is getting the record's temperature. So these two are solid. But this is something that we are doing here too. So this temperature should be passed here. Get relative humidity for this temperature for this dew when the saturation is this. So you don't do monkey business like this. This becomes dew. Dew is the same. Dew is actually the same structure as this one. Just dew. So then you don't do this. You don't do this. You just use them. This is just a convenient way. Records index done. Temperature is this. Saturation factor is temperature. In fact, this should be temp. And then get RH should be temperature. This should be what are you doing? This is dew. That was something. Okay. So now when temperature is less than 0, what are we doing? We are doing this yn, which is h, and h is calculated how? And I said, yes, if saturation factor is 1, I'm looking for this to be over 75. If saturation is, if it's more than 1, I'll do something. Otherwise, it's 1 or can it ever be 1 or less? Well, in this case, it can't because temperature is less than 0. It's not going to go in the other directions. If it's highly saturated, it's this, which is essentially this, but you get relative humidity for whatever that saturation is. You check if it's about thresholds. If the saturation is more than 2, you want this to be more than 50. It's like this. Otherwise, when saturation is equal to 1, it can't be 0. Unless temperature is exactly 0, which is covered here, so it can't be 0, but it can be 1. So this is the one case. Then in that case, we want the relative humidity to be over 75. This is it. Okay, run this. And kind of don't know what to expect at this point, but I see a lot of ones here in the first it's as if it's snowing here on the 14th hour, the first day of January. According to this, it kind of makes sense that it's supposed to snow. So here's what I'm going to do. I have almost 8,800 records. I will go somewhere in the middle, like 4,400. It's sort of June, July, right? And I would expect to see these guys to be zero. In fact, most of the time I would expect to see sort of April, May, this area to be zero too. It's consistent. Anything else we'll figure out. I would expect to see maybe some ones here, because these are the last days of the year. Yeah, see? Some hour it's snowing. In fact, these 2 hours are snowing. 3 hours. Good, good, good. It snowed that day. I would expect somewhere here to have less snow. Not, then I will fine tune values. This was really a snowy day. It's hard to believe it. When does it start? 8697. 8697. 20 hours snow. 24 hours still snow. We had snowy days like that too, and then 9, 7, 35 hours snow. How far off are we from 8800? Oh, so the last 2 days. Okay, so I can actually check that. 87. I'm looking at column P. No snow, and somewhere 8, 6, 9 something there was snow. It's not marked here, but based on my calculations, yeah. Because look here, I'm saying this is high. I think maybe that's the problem. I already had here too. This is not differentiating here. I'm gonna have to fine tune this another night. This is good. Um, it definitely works for temperatures colder than -10. We may have to fine tune the range between -10 and 0. Over 0, there's a whole other probabilistic equation here. I haven't actually checked that in the data, but I'm confident it will work. We are talking about, I think I could quickly check for that. We're talking about temperatures that are sort of here, the first hours. Let's do a quick check. 0, which is kind of okay with the real data because it's not marked snowy. However, according to the calculator or the article, something, actually no, we decided, um, their calculator showed for this one to be 75. We are too far off. That's what we decided. When this is close, then we are increasing the chance, and that closeness is based on these two, which isn't close. So it's just not dry enough. Like there was something weird. And then when it quickly gets wet, it turns into rain. There's a narrow area here. When it's over 0, you have precipitation. So this is a rare case. It might happen, but we are actually accounting for it too. And naturally, a part of this function, or this, will have to be done for cases like this, so that we determine, okay, there's precipitation, but it's not snow, it's rain. In other words, this much high, like RH being this high, we would like to see precipitation. We do know there can't be snow, therefore we will say there is rain. And in fact, historically, there is rain. So we have to extend our model to account for it. But as far as snow determination goes for this near 0 temperatures, it's okay. For -10 and below, I think it's okay too. I have to adjust something for -10 to 0, and we can move forward. But that's it for today. And I don't know when we'll tackle this next, but that's it for today. And most likely, I will do a devlog to summarize these findings. If you're finding it difficult to follow the important bits over many hours of live stream, there's some value here, but maybe summary is better worth. Like it's worth your time. So we'll see. Cool.